Good evening, my dear NEET warriors. Welcome to the one-shot detailed session marathon of kinetic theory of gases and thermodynamics for your NEET 2025 examination. Even a NEET 2026 student can watch this, of course. And this chapter alone, these two topics alone will fetch you easily for two questions, bare minimum. Sometimes there are instances where there were up to 3 to 4 questions, direct or indirectly, which means bare minimum 8 marks and up to 12 to 16 marks just from today's marathon alone. So obviously nobody wants to miss even a single mark because NEET 2025 or even 2026 will be so competitive. We know more than 20-25 lakh students will be writing it, and one mark will mean thousands and thousands of ranks. And obviously the seats are barely a lakh. So we need to make sure that we are giving our 100% for every single mark. The battle is on. Welcome, Atluru. Hi, Team K. Hello, Disha. Hello, Krishna. Welcome. Nice to see all my lovely old students back. Hi, Sridhar. Good evening, Bharati. Evening Star. Welcome, Aksu. Hi. Good evening. I'm very good. Nice to see all of you. This is your Captain Shreyas, and we are going live on the number one NEET English channel in the country. And this is the channel for you for your full complete preparation. So if you're not yet subscribed, subscribe it right away, right now, and let YouTube know that you are a NEET aspirant. So keep me away from distractions. And how do you tell YouTube? By liking this video. All right. So YouTube understands then you are a NEET aspirant. Thank you so much. So here for more than 13 years teaching all the kids. I love physics, love teaching. That's the reason why you find Shreyas sir, on all the channels, be it NEET, J, and so much more. Good evening. Hi Sanjay. Hi Sabreen. Hi Trial. Nice to see all of you. Hi Krishna. Good evening. Hi MBBS. Anushri. Good evening. Good evening. Now, when we talk about this chapter, usually these two units, or rather these two topics, are taught together because they are having some interdependencies. It can be taught in continuum. When we discuss this chapter, we discuss mainly gases. Yes, we mainly discuss gases. We generally do not discuss solids and liquids, although some principles of thermodynamics can definitely be applied to solids and liquids also. Now, this first part, which is kinetic theory of gases, was given, hundreds of years back, almost 200-300 years back, where by using Newton's laws of mechanics, basic understanding of kinematic equations, basic understanding of physics, scientists and physicists were able to predict how a gas behaves. Now, when I say or when I talk about a gas, what comes to your mind? It is free flowing. It will occupy this entire space. It has some volume. Obviously, it will be hot or maybe cold, means it has some temperature. Also, it will have some pressure because whenever gas is there and it's in a container, in a balloon, inside a room, wherever on your atmospheric gas, it always has some pressure which it exerts on the surrounding objects. So things like these, pressure, temperature, volume, and so much more, internal energy, which we'll be talking about, all these are the properties of the gases. And we generally do not discuss what is this molecule doing, what is that molecule doing, why is it our headache. No, we do not discuss individual molecules, but we discuss something called as the bulk property. Whenever I say the temperature of the gas, it's never the temperature of a molecule or of this molecule or of this molecule or this particle. It is the overall perspective, right? So it's just like, imagine you are from some school and we say, oh, this school, you right, this school is very good in sports, or this school is very good in dance or cultural activities, or this school is very good in producing toppers, or this school is very good in this, or this school is not good at all. So when I say, this school is good in sports, does not mean everybody is good in sports. Most of them are good in sports, or some might not be good in sports, something like that. So we discuss the overall perspective, the overall picture of a gas, things like temperature, pressure, volume, entropy, internal energy, and so on and so forth. All right. I hope this is clear. But the best part is all these laws of the overall picture comes from understanding how these molecules work, with respect to each other. So what are those laws or those postulates or those theory points which were given hundreds of years back? These are the pointers. The kinetic theory of gases explains the behavior of the gases at molecular level based on the following assumptions. So this started by noticing the molecules, and then it describes the complete picture. The gas molecules are going to be very large in number. Whenever you see a gas, I mean, it's not going to be 10, 100,000 or lakhs or even crores. It will be in billions and quadrillions and trillions of molecules are there even in a small space, even in a small can of gas. And these molecules are not going to be at rest. Rather, they are completely moving. Yes, this chapter will be taught from basics, Kamlesh. Yep, yep. Okay. So we'll be discussing questions model. Not necessarily all the PYQs. I'll be conducting separate PYQ sessions altogether. All right. I hope, Sukanya, that is fine. Like I said, we'll be having a nice problem solving sessions in the days to come. All right. And whenever you look at these molecules, they are not at rest, they are moving. It's not like statue, they are not at rest, they are moving randomly, they collide with each other, they have speeds, they have kinetic energy, they will hit, they will collide, and then they will disperse. Again, they will hit some other molecule, they will collide, they will disperse somewhere, they will again hit, they will hit the walls of the container. So this random motion occurs, and this randomness is always there. It's not like all the molecules decide to go in one direction. No. If there are 1 million molecules going left side, another 1 million will be going right side. If 1 billion molecules are going up, a billion molecules will be going down. They will average it out. Keep this in mind. These molecules are randomly moving. They have random speeds. They have, all, and it's not like everybody has the same speed. Some molecules will have more speed. Some are very slow. Some are decently paced. Just like in a class, not everybody gets 100 marks. Not everybody fails. Everybody on an average will score something. Maybe some classes might be better than one of the other classrooms, but overall, not everybody scores the same thing. If it is being done, then most likely they have cheated. Okay. Also, the molecules of the gas themselves are very small. So when I say the volume by a gas, it's not the volume of those particles, because those particles have negligible volume. It is the volume of the container, the space which contains that gas. It is that emptiness which we talk about as the volume, because the particle sizes themselves are negligible. And also, remember, the collisions of the molecules with each other are elastic in nature. Do you remember elastic collisions from momentum and collisions? Thank you for lighting up the chat box. Shakti, the session will be for 4 hours at least. Yeah. Do you remember elastic collisions? Yes, elastic collisions between the molecules. Basically, energy is not lost, energy is conserved. So that is basically elastic collision. So the molecules do not lose energy, they keep colliding with each other as well as the walls of the container. And when these molecules are moving, these molecules might be charged, uncharged, doesn't matter. They are obviously made of protons and electrons, but overall, they do not exert any forces because the distances as compared to the size is very large. So they will not experience any force. So the molecules will keep moving in a straight line path until they collide, and then they disperse, and they'll again travel in straight line and hit another molecule, disperse, and again they will hit something else. There is no intermolecular forces. This is a very important assumption for ideal behavior. Well, most of these assumptions are approximately also true, because if imagine you take a very small container, then the molecule size also will matter. If it's a very large container, then yeah, fine, the molecule is very small as compared to the container. But if the gas itself is in a very small space, the size of the molecules will matter. Also, if the molecules are very close by, then they will exert intermolecular forces. So this idealistic behavior only happens under certain conditions. Only happens under certain conditions. That's what you need to understand. The molecules obviously have kinetic energy, and each molecule will have different speed. That means all the molecules will not have same speed, not have same kinetic energy. They will be moving randomly. Overall, average kinetic energy will be there, that average kinetic energy helps me understand the temperature. And why not see a simulation to make you realize this whole postulates? Look at this. There is a chamber, there is a thermometer, there is a pressure gauge over here, there is a pump by which I can inject the molecules inside the container. So let's inject these molecules inside this particular container. Obviously, we need a lot of molecules. You can see the molecules themselves have some size. Obviously, the molecules themselves have some size. Now, these molecules will randomly collide with each other. The walls, they will distribute themselves, they will space out, they will even out. Initially, it felt like they are accumulating somewhere, but then you can see they will fill up the entire space. Now you can see some are very slow, some are very fast, and you can draw a graph of how many molecules are there for a particular speed. You can see this particular graph, it goes up and then comes down. Here the speed is less. Maybe there are some 20 molecules with low speed. You can see with maybe medium speed, there are more molecules. Average speed, almost even more molecules. Very high speed, less molecules. Very, very high speed, even less molecules. Very, 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 very high speed, very, very, very few molecules. So you can see how the speeds are getting distributed over here. Most of the molecules, you can see maybe 50 to 100 molecules are having a certain speed, but maybe 5 or 10 molecules only have very less speed, and maybe even 2 3 molecules have very, very high speed. So most of the molecules have a decent speed. Very few molecules will have very high or very low speeds. Is this absolutely clear, my dear warriors? Old memories. All right, looks like J English from 2022. Hello, Evangeline. Nice to see you guys. Thermodynamics also included. Yes, Bharat, definitely. Yes, Krishna, nice animation. Thank you, Disha. Great. Now, imagine if I start heating it or if I start cooling it. If I cool it, see what happens. The molecules are becoming slower. You can see the speeds are becoming less. The temperature is going down. Pressure is also going down because the speed is less. So they are exerting lesser and lesser pressure. Can you see the speeds have gone down? See how the graph has shifted towards the left side. Why did it shift to the left side? Because the speeds are becoming less, isn't it? The speeds have become less now. Now, even you can plot the kinetic energy. See, this green part shows how many molecules are there for a particular kinetic energy. The kinetic energy is on the lower side. Very few molecules have very high kinetic energy. Y-axis has number of particles, x-axis has kinetic energy. Let me start heating it. See, the temperature will go up. You will start seeing the molecules will begin to collide. That is what happens. When you heat something, the temperature increases, means the average kinetic energy of the molecules will increase. Every molecule you will see starts increasing their speed, so their average will also go up. So you can see the molecules are now quite faster. Can you see the kinetic energy has gone towards the right side? Can you see the speed values also are towards the right side? If I heat it more, you will see the speed will increase. You will see this graph will shift more towards the right hand side. Wow, it's gone really hot now. It's really hot, and you can see how the speeds have shifted towards the right side. I hope this makes it absolutely clear on how gases behave when you change the temperature or the pressure. Also, it gives you an understanding why kinetic theory of gases is the way it is. Now, a very important question. Think and tell me, whatever we said is an ideal behavior. In reality, the gas molecule size matters. Also, you will see the collisions will not be completely elastic. Inelastic collisions are there, definitely. Also, intermolecular forces are also there. So because of which the real behavior is slightly different from what we study in our textbooks, which is the ideal behavior. Can you tell me, under what situation or condition will a real gas behave like an ideal gas? Quickly think and tell me in the chat box. When will a real gas in real nature outside behave like an ideal gas? What should be the condition? Should there be some restriction on the pressure or temperature? I think there is. Quickly think. No, it's not STP. No, STP is not the answer. STP is standard temperature pressure. No. I think for the size and the interaction to be negligible as compared to the chamber and their distances, I feel there should be lot of space between the molecules. So let me make it open. So let the molecules escape out. Okay. For this to happen, yes, what should happen? At very high temperature or very low temperature or very high pressure or very low pressure. Yes, the session PDF will be there by tomorrow. Don't worry. Yep, the session PDF will be there. What should it be? Come on. Come on, my dear warriors. Yep, at low pressure and high temperature. Yes, the pressure should be low because if the pressure is high, then what will happen? The molecules will come close by. If the molecules come close by, they will start interacting with each other. And that is what you don't want. Also, the temperature should be low. If the temperature is high, they will collide more often inelastically and they will start losing their energies. Also, at very high temperature, maybe the molecules, because they are coming close more often, that's why they will interact more. You want to reduce their interactions. Hence, you should have, yes, low pressure and sorry, my bad. I told it opposite. My bad. For low pressure, high temperature. At high temperature, it is fine because the molecules will collide more frequently. They will go out. But at very low temperature, they will come close to each other. If the temperature is high, fine, they might collide, but they will immediately disperse because of the high kinetic energies. For low temperature, what will happen is the molecules are not having enough energy and they will start coming close to each other. They'll start sticking to each other, and that is what you don't want. So that is the reason why high temperature and low pressure. Very good. Awesomeness. Great. So let's come back over here. Let's come back over here. Now, looking at this, there is a derivation which you have in your NEET, not in NEET, in the board examinations, not important from the NEET perspective, where what happens, I'll tell you. You take a cube, this is a derivation based on the assumptions which is done. You take a cube of, let's say, side L, and you take molecules, each of mass m. So let me just duplicate this. Molecule, the mass of the molecules, is basically going to be m, and their speed will be nothing but v. This v will have three components, of course, because it can be moving in all the three dimensions: vx, vy, and vz. Like that, there will be many molecules, but all the molecules are same. Let's say hydrogen, argon, neon, oxygen, whatever. Masses will be same, but speeds will be different. So it will be like V1, then V2, then V3, V4, like that. There will be n number of molecules. What is n? N is basically the total number of molecules. Total number of molecules, the total number of molecules. From this, you can also get small n, which is nothing but the moles, the number of moles, which is the number of molecules divided by the Avogadro number. What is Na? It is the Avogadro number, Avogadro number, Avogadro number, which is 6 into 10 to the power 23. So from that, you will get small n, which is also the number of moles of that particular gas. Not just that, you can also get the mass of the molecules. This particular mass of the molecule can be written down as capital M divided by Na. Now, what is this M? This M is the molar mass. This is your molar mass. So imagine oxygen's mass is 32 grams. Okay, oxygen molecule's mass is 32 grams. You convert it into kg. So 32 into 10 to the power negative 3 kgs. Divide it with the Avogadro number. You will get the mass of each molecule. Because 32 into 10 to the power minus 3 kg is the mass of 1 mole of oxygen gas. So 1 mole has these many number of atoms or molecules. So each molecule or atom will have the molecular mass, molar mass divided by your Avogadro number. So that is how you get the mass of a molecule. These are the things which will be needed for you. Yes, I hope this is clear. Yes, Rocky will be doing 100 important questions and all of that very soon. Don't worry, we'll do it. Yeah. Now that you have understood till here, my dear warriors, the next thing what happens is they start analyzing how much impulse is each molecule applying on the surface. Remember, whenever any mass, whenever any mass is moving like this and it hits, let's say, a surface over here, it hits, let's say, a surface over here and it rebounds elastically. So because of that, there is a change in there is a change in there is a change in momentum. And because the momentum changes, that means what? There must be some kind of impulse. Therefore, there must be some kind of impulse. And that impulse which acts per unit time gives me the force on the molecules, or on the wall. Whatever wall exerts, same force wall will experience by Newton's third law. So this is the force exerted on the molecules or on the wall. And then what I get is that force. In fact, there will be many forces. The sum of all those forces upon that particular area gives me nothing but the pressure on the walls, which is also the pressure of the gas, which is nothing but the pressure of that particular gas. So that is how you can derive the value of the pressure of the gas using this simple logic. And this particular thing comes out to be very, very important. Let me write it down for all of you. Pressure into volume is 1 by 3 number of molecules into mass of each molecule into something called as RMS velocity square. This is a very, very important formula. This is what you get after, doing that complete derivation. I hope this is absolutely, absolutely clear. Now, what is this VRMS? I will come to it. But for now, just remember P is pressure. Obviously, let me write it down for you. Let me label it for you. P is nothing but pressure. It is not momentum. Don't get confused. V is nothing but the volume. Small m, I have already told you over here, right over here, mass of the molecules. Capital N is the total number of molecules. Now, what is this RMS? This is also called as the root mean square speed. Now, what is this root mean square speed? Did I not mention all the molecules have different speeds? There are many molecules. Some molecules have very high speed, some molecules have low speed, right? So, which speed do I take? The speed that you consider is called as the RMS velocity, root mean square, root mean square. Now, what is this root mean square? Simply put, go in the exact opposite direction. Yes, start from here. Yes, square, mean, and then take the root. Perform exactly in the opposite direction of the reading. So, whenever I say RMS, first take the square, then take the mean, then take the root. Because every molecule will have different speeds. Remember, there will be some molecule with a very small speed, some molecule with a very large speed, some molecule with a medium speed, some molecule maybe okay speed. Okay, so like that, there will be different speeds. Let's say this is the nth molecule with some speed. So first you square all the speeds. What you done? First you have to square all the speeds. So V1 square, V2 square, like that till Vn square. Next thing what you need to do, mean. Mean means average. Mean of something, mean height, mean length, mean marks, means average. So when you take average, what do? You add all the numbers, and divide it by the number of values that you have taken. That's it. Last thing, take the root. That means you just put a root symbol over here. That's why root, mean, and the squares. That is the meaning of root, mean, square, speed. I hope this is clear. Bhavya, I have already made a video on the channel regarding the low weightage. If you have not yet seen, basically these are the chapters which you can skip. Uh, where did it go? Somewhere here. Ha, these were deleted topics. I think I had made. Oh, it's not yet being put. Okay, I will put it. I think that short is not yet there. I'll make sure that the short comes up, Bhavya. Okay. Thank you for reminding me and mentioning it. Great. So let me block this off for all of you just to give you an example on the root mean square speed. Let's just do some quick questions on this. Example. Imagine if I tell you the values, the speeds of molecules are 2, 4, 5, 1, and 2. And let's say 3 and 2 and 1 and 2. Oh, okay, not needed so much. Just this much is enough. Okay, the question is, can you find the RMS speed? Can you find the RMS speed? Definitely we can. What you need to do to find RMS? What you need to do to find RMS? Let's try this out. RMS value will be root of, take the squares of each number. So 2 square, 4 square, 5 square, 1 square, 2 square. Then take the average. That means you add all of them and divide it with the number of samples. 1, 2, 3, 4, 5. 5 things are said. So divide by 5 and in the end put the root symbol. Okay, so what are we going to get? We are going to get 4 over here, 16 over here, 25 over here, 1 over here, and 4 over here. And the whole thing will be divided by 5. All right. Now, this thing you can do. 1 plus 4 is 5. 5 plus 25 is 30. 30 plus 16 is 46. 46 plus 4 is nothing but 50. So this will be nothing but root of 50 divided by 5. 50 by 5 is nothing but 10. So root 10 will be the answer, or you can just probably leave it in the decimal form, something like it will be 3.1, 3.2, around that. Okay, I hope this is absolutely clear. Everyone, so this is how you find RMS. RMS. Okay. So next question coming up on your screen. For an ideal gas, if all the speeds are doubled for the molecules in the container, for the molecules in the container, then the RMS speed will become how many times? The pressure will become how many times? That is the question. How many times will the pressure change? How many times will the RMS value change? That is the question. Let's see if you can figure this out. Come on, all the answers in the chat box. At least the first answer should be there quickly in the chat box. If the speeds of all the molecules are doubled, then what do you think will happen? If the speeds of all the molecules are doubled, very good. Most of you answered the previous question. Keep answering it like that. Some of you are saying pressure will be made 4 times. What about RMS? Think logically. Imagine if your VRMS in the first case is root of whatever V1 square plus dot 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 Vn square divided by n. Now in the second case, V double prime RMS will be, all the speeds are doubled. So this will be 2 times V1 square, 2 times V2 square, like that, 2 times Vn square, whole thing divided by n, of course. So what will happen is, 2 square is nothing but 4. So root of 4 will be there. And again, you will have V1 square, V2 square, like that, Vn square, whole thing divided by n. 4 has been taken out common from everywhere. Root 4 is nothing but 2. And what is there inside? That is nothing but your RMS speed in the first case. RMS speed in the first case. So RMS speed has become how many times? 2 times. 2 times. RMS speed will become doubled. It will be doubled for sure. It will be 100% doubled. Yes, a lot of people say that it has become 4 times because the thing RMS has square inside. But do not forget, there is also a root. Okay, so that root and the square end up cancelling out each other. Next, pressure. We know this equation, PV is equal to 1 by 3 Nm VRMS square. So if the RMS speed is made 2 times, the square of it will be made 4 times. Number is not changing, mass is not changing, 1 by 3 is a constant, volume will not change because it's a container. So what will happen to the pressure? The pressure on the left hand side should also change 4 times. So it will become quadruple. It will be quadruple. Is that clear? Understood? So pressure will become 4 times, RMS speed will become 2 times. Great. Yes, Sukanya, I knew. Many people forget that root. Always remember the square. Okay, great. No issues. Moving on to the next thing. Is there any formula for the RMS speed itself without having to know the pressure and the other things? The answer is yes. Now, see guys, what happens is when you see this particular equation, PV is equal to 1 by 3 N M V R M S square. Let me tell you what we can do over here. This N, I can write it, or rather just keep that N. This M, I can write it as molar mass divided by Avogadro number. Molar mass divided by Avogadro number. VRMS, or else do one thing, just leave it like that. This N, I can write it as small n into Avogadro number. This n I've just written in down as n into Na. If you're wondering how it came, just go back a little bit over here, then you will understand. Small n is capital N by Na. So capital N will be small n multiplied by Avogadro number. So from here, I'm writing it down. And then just, sorry, this is 1 by 3. Then this is just m into VRMS square. What I will do over here, deliberately, I will just put the number 2 below. So to preserve the equality, I will put 2 over here. I'll just put that number 2 over here. All right. Now what I will do, I'll write small n over here. Then I will write basically 2 by 3 and then your Na over here. All right. And then this is nothing but half mv RMS square. What is this exactly going to be? What is this exactly going to be? Mass times RMS speed square into half. It looks like the average kinetic energy because this is a complete picture of the net molecules. It is not the speed of any one molecule. It is a root mean square speed. So that is going to give me basically the average kinetic energy of that gas. Oh, and I had told you this before only during discussion of the postulates. Temperature and kinetic energy. The average kinetic energy of the gas molecules is proportional to the temperature of the gas. Everybody agrees? It is proportional to the temperature of the gas. So using the kinetic theory of gases, it will be N into 2 by 3 Na, some constant into temperature. This is some constant. So now I will write this as this number, this number, this number, this number, all these are constant. That constant as a whole is R, and this is P, and this is basically P into V. So that's how you get the ideal gas equation without experiments. This is theoretical proof of ideal gas equation. Crazy, right? Mind blowing. Never did you know that ideal gas equation can be derived without even Boyle's law, Charles' law, Gay-Lussac's law, nothing required. Directly you can derive it using basic principles of kinetic theory of gases, which is based on mechanics principle, Newton's laws, nothing else. So PV is equal to nRT. You might be wondering what the hell is this R? Well, this R is nothing but your gas constant. It is nothing but your ideal gas constant, and the value of R is nothing but 8.314, or you can just keep it almost 8.3, and that is nothing but joule per mole per Kelvin, joule per mole per Kelvin. You can also keep it approximately as 2 calories per mole per Kelvin. Usually in physics we use joules or calories. We generally do not use liter ATM because that is more prevalent in chemistry. This is your ideal gas equation. This is your ideal gas equation. Keep this in mind. This is absolutely clear, my dear students. Perfect. Awesome. Great. Now we can play around with this a little bit more, of course. We can play around with this even more, and you can get even more equations like, for example, PV is equal to nRT. Now, you can also write volume and get rid of volume and write in terms of density. All right. So, you can also write it as PM is equal to rho RT. PM is equal to rho RT. This is also a very valid equation. From this only you can get it. From this only you can get it, where density is nothing but the mass by volume. Number of moles, you can write it as, you know, the number of molecules divided by Avogadro number. So you just play around with this equation a little bit, you will get basically this equation. So this rho over here stands for the density of the gas. This stands for the density of that particular gas. This is also a very valid equation. PM is equal to rho RT. Okay, I hope this is absolutely clear in everybody's head. Now, coming back to our previous question, saying, can we write RMS speed without knowing the values, without knowing the pressure or the volume, without using this equation? Can I find out the RMS speed? The answer for that is yes, and I'll tell you how. You can just write this as, you can just basically write this particular RMS speed, this particular RMS speed. Okay, what can you write it down as? This can be written down as root of 3 RT divided by M. Yep, this is the general formula for RMS speed uh, for an ideal gas only. Okay, and if you do not want to calculate it with the individual values or with pressure and volume values, so if you want to find it when the temperature is given, then you usually use this formula. Okay, I hope this is clear. If pressure, volume is given, number of molecules is given, etc., then use PV is 1/3 nmv square. If values are given, then use V1 square, V2 square, V3 square divided by n under the root. If temperature is given, molecular mass is given, then use this formula. So based on case to case, you can use any of these formulas, but usually you will see many times you will be using this formula only. So I'll just block this up. What is M? I will repeat it again over here also. M is nothing but your molecular weight. Molecular weight, basically your molecular mass. Molecular mass. R is your gas constant. T is temperature in absolute scale. Yes, this is nothing but your temperature in absolute scale, like Kelvin scale. Kelvin temperatures are absolute. Remember, Celsius, Fahrenheit, They are not absolute scales. So Kelvin is what you should put over here. Now, this also tells me one interesting thing, that at the lowest temperature, at the lowest temperature, and what is the lowest temperature? Which is minus 273 degrees centigrade, which is nothing but 0 Kelvin. What do you think will happen? What do you think will happen? Temperature is 0. RMS speed will be 0. RMS speed will be 0. That means that all the molecules are at rest. All the molecules are at absolute rest. They are not moving at all, which is not possible. No matter what you do, some sound will come, some light will fall, some vibration will come. The molecules will, for sure, 100% pakka, they will vibrate here and there. There will be some motion. That is why it is very difficult to achieve 0 Kelvin or negative 273 Kelvin. Understand that. So otherwise, when you heat the gas, or else when the gas is heated, when the gas is basically heated, then what happens is the average kinetic energy increases. The average kinetic energy increases. So that's why their RMS speed will also go up. Yes, and that is how even the temperature will rise. The temperature rises. So this is what happens when once you heat it, when you cool it, RMS speed, temperature, average energy, everything will come down. Okay, I hope this is absolutely clear. All right. Not only is the RMS speed 0 at the lowest temperature, but even the average kinetic energy of the gas molecules will be 0. Yes, average kinetic energy will also be 0. These are some important pointers. Now, remember in that simulation which I showed you over here, remember there was a graph of the speeds and you saw the speeds became very large. Sorry, a lot of molecules had a particular speed and then very high speeds were there with very few molecules. So this graph is a general graph. Even if I cool it or heat it, doesn't matter, the graph nature will be same. Yeah, the graph will shift towards the left or towards the right. That is okay. But the nature, the shape of the graph is almost like a bell, is almost like the bell of a temple or just the bell of a school or the general bell shape. That is why it is also called as a bell curve. It is also called as a bell curve. So there was this law given by Maxwell, and that's why it is also called Maxwell speed distribution. Maxwell's speed distribution, where on the y-axis you plot the number of molecules, and on the x-axis you plot how much speed do they have. You will see that the graph will roughly look something like this, like a shape of a bell. Okay, that is why it is also called as a bell curve. This might be at some, let's say, low temperature, but the moment you increase the temperature, the graph will shift like this. So this is going to be at a higher temperature. As the temperature rises, the speeds will go up. You will see very few molecules have very low or very high speed. Most of the molecules have a particular speed, and this speed, which most of the molecules have, this is also called as the most probable speed. Most likely or most probable speed. If you look at the molecules, if you see 100 molecules, maybe around 50 to 60 molecules will have that speed. That is why it is more likely you encounter them. Yeah, you will encounter very high and very low speeds, but they will not be so much as these molecules. So that is the most probable speed. And this most probable speed value is going to look very similar to this formula, is going to look very similar to this formula. Instead of the number 3 over here, you have the number 2. It is root 2 RT divided by M. Root 2 RT divided by M. This is the formula for the most probable speed. Is that okay, my dear warriors? Yes, the graph will shift. Crystal clear. Very good, Nihal. Awesome, Disha. Awesome, Krishna, Atluru. Very good, Sukanya. Clear. Awesomeness. Now, there is also the last part, which is the average speed. The average speed, very different from RMS speed. Average, or basically just the mean speed. This average speed is just literal average V1, V2, V3, like that, Vn, the whole thing divided by n. There is no square, there is no root. This value comes out to be, you have this formula, it looks very similar to that. Yep, very easy to remember because their usual looking is similar. Here it will be root 8 RT divided by pi m. It is 8 RT by pi m. Yes, so that is your average speed of the molecules. So you have got now all the three speeds: average speed, most likely speed, and the RMS speed. Obviously, out of these three, since R, T, M and the root are common, the only thing which has changed is these numbers 8 by pi, 2 and this number 3. Out of these numbers 3, 2 and 8 by pi, who is the highest? Who is the lowest? It's not that difficult to see because 8 by pi, 8 and pi, come on, pi is 3.14. So 3 2s are 6, 3 3s are 9. So it will be between 2 and 3. So this number will definitely be, in between most probable and the average values. So you will see that the most probable speed will be the lowest. So the average speed will be somewhere in between. So let me put it like this. The most probable speed will be the lowest, and the highest obviously will be the RMS speed. Highest will be obviously RMS because RMS had that number 3 in it. 3 is the biggest out of all the three. 3, 2, and this is something like 2 point something because 8 by pi will be 2 point something. Is that clear, everyone? Awesomeness. The weightage of this chapter I have already mentioned at the beginning of the class, around 2 to 4 questions. 2 is bare minimum, 4 maximum. Indirect questions can also come coupled with some other chapters. Yep. Okay, great. So keep these things in mind: Maxwell speed distribution, average, most probable, RMS speeds, and all of that. Okay, the key formula is also mentioned over here, and also the gas laws which were derived for all of you. Cool. So how about doing some questions based out of this before we go ahead? Here is the question. Find the ratio of temperatures for hydrogen and helium gases for which their RMS speeds are equal. For which their RMS speeds are basically going to be equal. So let's try to do this particular question, my dear students. Find the ratio of the temperature for which hydrogen and helium, both these gases, RMS speeds are equal. Okay, first of all, let's write down the formula of RMS speed. RMS speed is root of 3RT divided by M. Now, who all are going to be different in this? First of all, ratio of temperatures is asked, so T will be different. RMS speeds are equal, molecular masses will be different. So 3 is same, R is same, RMS speed is same, only T and M are going to be different, which means root of temperature of hydrogen by molecular mass of hydrogen will be root of temperature of helium by molecular mass of helium. Is that right? Because their RMS speeds are equal. So whatever is there inside the root should be equal. Hence the ratio should be equal. Roots are same. Yes. Direct formula based questions will only come. Okay. Yes. Uh, Sridhar, it's really sad that you had to go through this, and I'm really sorry for your loss, but I really hope that you set an example there and you make your father proud. And I'm pretty sure he would be here, means he would also wish for the exact same thing, that you study and become a doctor. And I'm pretty sure he will be very proud from somewhere or the other when he sees you next year or this year, whenever you clear your NEET examination. And I'm pretty sure you will be saving more lives, and probably you will bring smiles on so many kids' faces whose dads or parents or grandparents or sons or whosoever relatives, friends will be in the hospital. So I'm pretty sure you are going to make a big impact, and that's how probably you can overcome this hardship which you are going through. And I really hope that God gives you all that strength and courage. Right. Okay. So this root will cancel, isn't it? Root will cancel. So TH by MH will be THE by MHE. But we want the ratio of the temperatures. So temperature of hydrogen by temperature of helium will be molecular mass of hydrogen by molecular mass of helium. What is molecular mass of hydrogen? Do not forget, this is a diatomic gas, whereas this is a monoatomic gas. Hydrogen will exist as H2, each having 1 as the atomic mass number. So H2 will have 2 atomic mass as the mass, and helium is as a monoatomic gas with 2 protons, 2 neutrons. The molar mass will be 4. So hence the ratio will be 1:2. Got it? Yes. My name, it's written right over here, Captain Shreyas, Instagram, Telegram, everywhere. Okay, cool. Yeah, awesome. Great. Now, now coming back to the next question coming up on your screen. Here it is. If the temperature of of oxygen gas at 300 Kelvin is doubled doubled, then its RMS speed is the same as the most probable speed of of hydrogen gas at which temperature? At which temperature? So you need to understand this question because it is framed in a slightly more complex way. You have to break it part by part so that you get it. Okay, let's break it part by part so we understand, you know, um, it properly. First, talk about the oxygen gas. It is right now at 300 Kelvin. Now, if the temperature of the oxygen gas is doubled, that means if you talk about for the oxygen gas, that 300 Kelvin is made to 600 Kelvin, then whatever RMS speed it has, so at 600 Kelvin, whatever RMS speed is there, this RMS speed is equal to, the RMS speed is the same as the most probable speed of hydrogen gas. This is equal to the most probable speed, but for hydrogen gas. But the problem is the temperature is not. Understood? Always break the problem into parts. If you analyze it, then you will be able to make a equation. You will be able to make the basic, equality, after which you can proceed. Okay. Now, coming back to the solution, what is the RMS speed formula? RMS speed formula root 3 RT by M. So over here, it will be root 3 RT. Temperature is 600. So put 600 divided by M. Be careful. This is oxygen. Oxygen has a molar mass of 32. I'm just interested in the number. I will not convert it into kgs and all of that, because I know whatever I do over here on the left hand side, same thing I will do on the right hand side. Eventually the units will cancel out. So that's why I'm not bothered about the units as of now. Going to the right hand side, most probable speed is 2. So 2 times R into temperature, which I do not know. Molecular mass of hydrogen, it is basically going to be 2 over here. This 2 and this 2 will cancel. Isn't it? This 2 and this 2 will cancel. R and R will also cancel. Even root and root will also cancel. My goodness. So what am I left with? 2 2 went, R went, root went. T is only remaining. On the left hand side, R has gone, root has gone, 3 is there, 600 is there, and this number 32 is there. So I think I have come very close to my answer. So temperature will be, well, you can do the math over here. 600 divided by 4 is 150. 32 divided by 4 is nothing but 8. 150 divided by 2 is 75. Right? And this divided by 2 is 4. 75 into 3. Right? So that will be 210, 225. So this will be 225 divided by 4, isn't it? Everyone? Yes, very good, Jason. Awesome. 225 divided by 4, not 225 divided by 8. Yes, correct. So that is what it is. So temperature will be 225 divided by 4 Kelvin. Yep, perfect. If you want, you can convert it into decimal also. Got it? Clear? Understood how to solve this question? Step by step, I have made you solve this particular question. So that's how you get the questions generally on these things over here. One more question which we can do. One more question. This was very commonly asked. This was very commonly asked. Okay. Find the ratio of RMS is to average is to most probable speed of the ideal gas. This is a very common question which was asked. Find the ratio of the RMS, average, and the most probable. Now just use the formulas. The formula is root 3 RT by M. The average formula is root 8 RT by pi M. Here the speed formula is root 2 RT divided by M. RT, M will cancel. So I'll be left with root 3 is to root of 8 by pi is to root of 2. So that is the answer to this particular question. Okay, root 3 is to 8 by pi is to root 2. Don't just remove the root. That is stupidity. Don't do that. Okay, you cannot just square these things and forget the root, because that option will also be there without the root. And many people will think, sir, root will cancel. No, sir. No, it can't be cancelled, because if you square this to remove the root, then it will be the ratio of RMS square to average square to a most probable square. That is not what is asked. The ratio of the squares is not asked. Just the normal ratio is asked. So do not square this. It will be a wrong answer. Okay. I hope this is absolutely clear. Perfect. Awesome. All right. So these were some of the questions which were there. Now, where is it? Yes, the mean free path coming now over here. Let me bring it. This is the next concept which is there. The average free path. Just imagine you are one of these molecules. Just imagine you will collide, you will travel, collide, travel, collide, travel. Your motion is random, right? Your motion is random. Let me cool it so that you can easily see it, because the speeds will be slower. Now, whenever you collide and then travel, you are traveling freely because you are not colliding. When you do dishum, collide. Again, next, it's like a reset and you again travel freely for some distance. Do you think every time you will travel the same distance before the next collision? Answer it in the chat box. Do you think every time you collide, Dishum, will you travel the same distance again before the next collision? No, right? Every time it will be different. Every time it will be different. Yep. So there are different distances which a molecule will travel every single time, but you will see on an average it will maintain something. There will be an average free distance which a molecule will travel. Obviously, if I heat it, then it will collide more rapidly. So I think the distance might change. Or if the pressure changes, the volume changes, the number of molecules will change. Let's say now there are very few molecules. Most of the molecules go out. Now they will collide very coolly, aram se, which means their average distance which they travel freely will be more. So that brings us to that particular concept of mean free path. Any particular molecule, any particular molecule will travel before hitting the next molecule, and these distances are random, but on an average it will maintain something. On an average it will maintain something that is called as the mean free path. Is the average distance of travel between between the collisions, between the collisions. The formula, the symbol for that is lambda. This is nothing but distance 1 plus distance 2 plus like that till distance n, the whole thing divided by the number of collisions. But there is a direct formula, you don't have to substitute these values. What's the formula going to look like? If the volume is more, lambda, which is the mean free path, will increase. So volume will come on the top. The next thing that you have is the number n, which is the number of molecules. This is not the same n as this over here, so don't get confused. Okay, so like that, I can just put over here d small n so that you are not confused. Okay, this is the number of molecules. It is there below because if more molecules are there, then it will have very less space to travel before the next collision. So average free path will reduce automatically. That's why it is in the denominator. If n increases, lambda decreases. There are some constants also like root 2 and pi. Yes, root 2 and pi. And there is one last thing, and that is basically the diameter of any molecule. The size of the molecule also matters over here. D, which is the diameter of the molecule. Diameter of the molecule. Why does this matter? Because if the size is big, obviously they will occupy more space. There is a good chance they will hit each other while they are moving. If the size is small, there is a good chance they will escape without collision along the same path. Obviously, if two bikes are traveling in a narrow road versus two cars are traveling in the narrow road, chances of the cars hitting each other are more than the bikes hitting each other because their sizes are bigger. So that's the reason why the size also matters over here, and d square is there below, because if d is more, lambda will decrease. So this is the formula, guys. Is that absolutely clear, everyone? What's the formula for the average free path? I will mention over here what is each and everything. V is nothing but the volume. D I have already mentioned over there. N is the number of molecules. Number of molecules out there. Okay, keep this in mind. Yep. You can refer to the Super 6 series. I have taught it awesome over there. Yep. Yeah. Great. Now, there can be some basic questions on this. There can be some basic questions on this. Like, say for example, in my goodness, in a container, in a container, if pressure is doubled, if the pressure is doubled, then what happens to the mean free path? Then the mean free path, then the mean free path will become what exactly? That is a question. Think about it and answer in the chat box. If the pressure is doubled, what happens to the mean free path? Yes, meanwhile, I'll just drink some water. Thank you for reminding. Some of you are saying decreases 2 times. Let's think about it. What's the formula? The formula is mean free path is volume divided by root 2 pi n d square. Let's think what will change in all of these. Root 2 and pi are constants. D is the diameter. None of them will change. Volume is also fixed because of the container. Because of the container, that volume also automatically becomes fixed. This n is also going to be fixed because there is no escape. There is no escape or no addition of molecules. So this also becomes very uh, clear that it is fixed in number. The diameter, the size of the molecules is also going to be a constant. Root 2 and pi, they are anyways numbers, so they are constants. So what should happen to lambda? It should also remain a constant in this case. That means it will remain the same. Lot of people I have seen make a mistake and they either write it as it becomes double or it becomes half. That is wrong, because what many people say, sir, if if pressure increases, pressure becomes 2 times, then the volume will become half time. Wrong. Container is fixed. In fact, volume will not become half times because pressure has doubled. The temperature will become 2 times and the volume will remain constant. Yep. So be careful. Temperature will double automatically. Lot of people make that mistake. Got it? This is a common question. Once there was a question where directly it was asked, what is the formula of mean free path? They had just changed these numbers. They had put n square d root 2, instead they had put 2 pi, they had put v by n by v, all those things. Imagine such a question has also come in the exam. They have directly asked what is the formula for mean free path. I mean, that would be the easiest question, but obviously it could be confusing at that moment in the examination hall. All right. Now, going ahead to the next concept, which is your kinetic energy of the gas molecules, law of equipartition of energy, and other things. So, to get to that, let's come to a thing called as, first of all, you know, uh, basically the concept of degrees of freedom. Yes, something called as degrees of freedom. But if more molecules collide, less distance average? No. What happens is, in spite of increasing the pressure, the temperature is higher. So because of which the speeds are higher, so probably they will escape that collision most likely. So maybe the pressure is higher, but doesn't matter. The mean free path has not changed. Okay, just the speeds have changed. Maybe they will move very fast and they are able to accommodate that increase in the pressure, right? Now the concept of you know what is it, degrees of freedom. Degree of freedom, this is the next concept which will be needed. Degrees of freedom. Now what is this degree of freedom? That is basically the independent motions, the independent motions which a molecule has energy associated with. energy associated with. The symbol for degrees of freedom is basically F, and there are multiple degrees of freedom which a molecule can possess. One is something called as translation degree of freedom. The next is basically called rotational degree of freedom. And the last is basically the vibrational degree of freedom. These are the three types of degrees of freedom which are independent motions which a molecule can possess. Just imagine, just imagine this. Okay, say for example, there is a molecule over here. Let's say like this. Just showing some random molecule. Don't get confused, sir. Is this hydrogen? Sorry, is it H2O? Is it helium? What is it? Doesn't matter. It's some random molecule. When I say translation, it means the molecule is either moving like this, or it is moving like this, or probably it is going in the Z direction. So it can be moving in the X direction, it can be moving in the Y direction, it can be moving in the Z direction. These are translational motions which are independent. The molecule can independently go up, it can independently go front, it can independently go left, right, like that. So that is why it's said to possess translational degrees of freedom. Similarly, when I say rotational degrees of freedom, what it means is the molecule, observe this carefully now. The molecule can rotate along the x-axis. It can rotate along the x-axis with some angular velocity. It can rotate along the y-axis with some angular velocity. It can rotate along the z-axis with some angular velocity. So that is basically rotational degrees of freedom. The molecule will rotate like this or like this or like this. So it can choose either the x-axis or the y-axis or the z-axis as the axis of rotation. That is all independent. They are completely free. They are not dependent on each other. They can independently rotate. And vibration means the molecules can expand, contract. I mean, the molecular distances can change, because of which there is vibration. So the molecules can expand and they can contract. Okay, something like oscillations. So it can definitely oscillate, and it can possess something called as the vibrational degree of freedom. Is this absolutely clear? Yes. Let's start with question practice next session onwards. Definitely, Krishna. Now, which molecule possesses which type of degrees of freedom? That is a very interesting thing to see. Let's study that properly. If you take something like a monoatomic molecule, a monoatomic molecule, example, helium, argon, all the inert gases, neon, etc. Such a molecule, if you notice carefully, observe this now, such a molecule, it can definitely travel in the x direction, it can definitely travel in the y direction, it can definitely travel in the z direction. It definitely has three independent motions which it can do, Vx, Vy, Vz. So definitely it has three translational degrees of freedom, DOF. But what about rotation or vibration? Vibration, what will it vibrate with? I mean, you need at least a pair of molecules or atoms to vibrate. I mean, molecules are going back and forth like this. So independent molecule, I mean, it will be just translating. Vibration, you need two molecules for either twisting or vibrating like this. Okay. So that is why vibrational degrees are not there. What about rotation? Well, that molecule can rotate, but there is a problem with that. Just imagine, if I have a big molecule, that's okay, but the molecules are like points, they are very small. Now, when this big sphere rotates, it has rotational kinetic energy. But imagine this sphere was teeny meeny, like a point, like a small point. If it is like a small point, if that point rotates, half I omega square energy will be negligible. It is of no use. Even if omega is there, I is negligible because it is a point mass. So there is no rotational energy. And what did I say? Degrees of freedom are independent motions, but it should have some energy associated with it. I hope this is clear. Yes, bond length should change. Correct. Jason, for vibration. So here there is no rotation or vibration degree of freedom. Why there is no rotation is very, very important for you to understand. It's because they are like point masses. And for point masses, the moment of inertia is negligible. So half I omega square. So because of which half I omega square will be negligible. When there is no energy, you will not count. When there is no energy, you will not count it. So hence, I will say for such things, the total degree of freedom for a monoatomic gas is just 3, right? It has basically how many degrees of freedom? It has 3 degrees of freedom. It has basically 3 degrees of freedom. Next, let's go to diatomic or linear polyatomic gases. Now, why both of them are combined together, I will explain you. Examples of diatomic gases: H2 gas, oxygen gas, nitrogen gas. Examples of linear polyatomic gases: CO2. CO2 molecule is linear, meaning the bond lengths are in a straight line 180 degrees. H2O molecules, it makes 108 degrees. It is not a linear polyatomic. Okay, I hope this is absolutely clear. Okay, so these are some of the examples. So let us show these molecules so that you understand really what is happening. So diatomic, something like this, and linear polyatomic. Okay, this is linear polyatomic or just a diatomic gas. What kind of degrees of freedom they can possess? Obviously, these can move along x, y, and z, x, y, and of course z direction. So definitely it has uh, 3 translational degrees of freedom. You can see that very clearly. Vx is there, Vy is there, and of course Vz is there. But what about rotation? This is the funny part now. This is the interesting part. Observe it carefully, my dear students. Observe it. If the molecule, it's like a dumbbell, just imagine 2 point masses like this with a bond length. If they rotate like this, the molecules are going in big circles like this. So when they are at some distance and they are rotating about an axis which is like this, so there is a decent amount of moment of inertia. I cannot neglect it. So the moment of inertia becomes considerable. It's not point mass spinning about itself. It is a mass revolving now. So when you rotate it along the y-axis, the molecules will go like this. So definitely their moment of inertia will be counted. Even if I rotate it like this with the z as the axis, then also it should be counted. So whether I rotate along the y-axis or along the z-axis, omega z, omega y, omega z, omega y, have a big revolution to undergo, big moment of inertia, decent kinetic energy of rotation, so it should be counted. But if I spin it along the axis, along the bond length, that's when the problem happens. These are now just point masses which are just spinning. These are just point masses which are just spinning like this. The masses are not going in big circles, they are spinning about their axis. The size is small, so their moment of inertia becomes negligible. So it only has 2 rotational degrees of freedom. 2 rotational degrees of freedom. Is this absolutely clear, my dear warriors? Yes, not 6. It has only 2 rotational degrees of freedom. What about vibration? Well, the molecules have some bond length. They can obviously change. They can go up and down. Now, whenever vibrational degree of freedom comes with one vibration, you will see it accounts for 2 degrees of freedom. So whenever there is a vibration, you will see it considers this mass also. So it accounts for 2 degrees of freedom. So usually at high temperatures only it happens, not at low temperatures. At high temperatures like 2000 Kelvin, 1500 Kelvin, 3000, 4000 Kelvin, which is normally not seen around us. So at high temperature, there will be two vibrational there will be two vibrational degrees of freedom. There will be 2 vibrational degrees of freedom. Otherwise, it is not there. Voice is low. Just check this, Nandu. Again, I'm so glad, Null, you're watching even the older sessions now. And I'm really proud that I did that, at one point of time in 21, 22. And still, students watch it because that is obviously one of the best contents which I had delivered. Thank you so much. Okay. I hope the voice is clear, my dear warriors. Just let me know quickly in the chat box. Yes. Okay. Perfecto. So usually, how many total degrees of freedom are there? So the degrees of freedom for normal temperatures for a diatomic molecule, as you can see, 3 from here, 2 from here. So it is basically going to be 5 degrees of freedom. How many degrees of freedom? 5. This is at normal or basically low temperatures, at normal temperatures, which is usually the case. You do not get high temperatures. The last thing over here is when you have a polyatomic non-linear molecules, non-linear polyatomic, non-linear polyatomic. So look wise, it might be something like this, like this. This would be the bond between them. Obviously, they can be moving in the x direction, they can be moving in the y direction, they can be moving in the z direction. So it can have Vx, Vy, and Vz. That means it has 3 translational degrees of freedom. There are many examples of this. H2O, CH4, and so much more. Methane gas. So many gases are there around us, which are basically, polyatomic in nature. What about rotation? Rotation wise, whether it rotates like this as the axis, or it rotates like this with the y-axis or the z-axis, each time their moment of inertia and the energy becomes significant, because these are molecules which will rotate round and round like this or like this or like that. And every time the molecules are going like a revolution, they are not spinning about themselves. So hence it becomes significant. So definitely in this case, it has 3 rotational degrees of freedom. In our syllabus, we don't study vibrational modes for polyatomic gases, so ignore that part. So totally for polyatomic gases, the degrees of freedom 3 and 3 will make it 6. That's the total degrees of freedom for a polyatomic gas. Is that absolutely clear, my dear warriors? Perfecto. Awesome. If vibration is effective in the previous case, yes, then +2 will come. So yes, this will become equal to 7 at very, very high temperatures. Yes, 5 plus 2, that will make it 7 if you go to very, very high temperatures. Now that we understand, okay, what is basically degrees of freedom and how much degrees do mono, dia, polyatomic gases have, what is it got to do anything with kinetic theory of gases? See, any gas hydrogen, helium, oxygen, nitrogen, H2O, whatever, CO2, methane, they all have different degrees of freedom, translation, rotation, vibration. They have some kinetic energies. So you might be wondering, is rotational energy more or translational energy more? Or is vibrational energy more? Now, you might be thinking, oh, maybe this is more, this is less, but nature does not distinguish or differentiate. It's not partial, it is completely fair. And what nature does is so beautifully, it says every degree of freedom will get equal amount of energy. It's so crazy. Nature does this. It says whether your translation and whether you have 2 or 3 or 4 does not matter. I will give every degree of freedom an equal amount of energy. And how much energy does each degree of freedom get in every molecule? Half kT, where k is the Boltzmann constant. What is that k? I will come to it. Each degree in every molecule gets the same amount of energy. So that's what is important over here. So we come to something called as the law of equipartition of energy, law of equipartition of energy, which says, law of equipartition of energy says that every degree of freedom in each molecule gets the same energy of half kT, where k is called R by Na. It's called as the Boltzmann constant. Boltzmann constant, which is the gas constant divided by Avogadro number. It is nothing but the gas constant R divided by Avogadro number. If you find that value, 8 by 6, it comes close to 1.3 into 10 to the power negative 23. That is the approximate value of the Boltzmann constant. 1.3 into 10 to the power minus 23. It's a very, very small value. So you can imagine if you substitute it here, and even if you keep the temperature as 300, 400 Kelvin, 400 by 2 is 200, 200 into this will make it 2.6 into 10 to the power negative 21. So that's how small energy is there in every molecule's every degree of freedom. So this is a very, very important law. Is that absolutely clear? So now, if you think about it, for say for example, for a monoatomic gas, there are 3 degrees of freedom. So kinetic energy in X plus kinetic energy in Y plus kinetic energy in Z, if you add them for every molecule, it will be half kT plus half kT plus half kT. So that means it will be 3 by 2 times of kT. This is always per molecule. This is per molecule for a monoatomic. Similarly, if you do it for a diatomic gas, there will be 3 translational degrees of freedom plus rotational, there will be only 2 degrees of freedom. So you will have half kT how many times? 5 times. So basically it will be 5 by 2 kT. Is that clear, my dear warriors? It will be 5 by 2 kT. Similarly, you can go for polyatomic gases and so on and so forth. So now I can generalize this. For a gas molecule with F degrees of freedom, the kinetic energy of the molecule is given by F multiplied by half kT. How many times? F number of times. F number of times. F is the degrees of freedom. But we know we generally do not talk about a molecule. We generally talk about the gas as a whole. Gas will have many molecules. Correct? A gas will have many molecules. Now, for uh, for the complete gas with basically n molecules, the total kinetic energy of the gas will be nothing but n multiplied by fkt divided by 2. fkt by 2, fkt by 2, for every molecule if you add, there will be n such molecules, so that's why multiplied by n. Is this absolutely clear till this point, everyone? Let me know quickly. Okay, now what do we do next? This kinetic energy of the gas will come out to be n is there as it is, multiplied by, you have degrees of freedom as it is, you have 2 over here, and you also have T over here. What the hell is this K? I just told you what is this K. K is nothing but the Boltzmann constant, which is R by Na, which is nothing but R divided by Na. Let me just move this around a little bit and you will see one very interesting thing happening. I will write N by Na first. Then I will write Fr by 2 over here, and then I will write T over here. Okay, N by Na, Fr by 2, and T over here. On the left hand side, this total kinetic energy of the gas is also the internal energy. Very interesting concept. See what happens when you talk about a real gas. The internal energy is the sum of kinetic energies and the sum of potential energies. What am I talking about? I'm talking about the internal energy. Internal energy of a gas. U. Internal energy. What is this internal energy? It is basically the total sum of all the energies of the particles of the gas, the particles of that particular gas. Is the sum of all kinetic and potential energies for a real gas. And this is for a real gas. Why is this potential energy there? Because of molecular interaction. Interactive forces are there between the molecules. That is why it is there. Why is the kinetic energy there? Only because of the motion. But the moment you go to an ideal gas, remember one thing, it's only the sum of kinetic energies because of the motion. This is basically going to be zero because there is no interaction at all. So the sum of the kinetic energies is just the internal energy. Is this clear? This is only true for ideal gas. For real gases, internal energy is kinetic plus the interactive energies between them. Which means over here, what should the total kinetic energy of the gas exactly be? It should be also the internal energy of the gas. And what's the symbol for internal energy? It is basically U. So now the last step coming over here, N by Na. What is N by Na? Come on, put it up in the chat box. What is N by Na, my dear warriors? Number of molecules by Avogadro number, that is number of moles, isn't it? What is Rf by 2? What is Rf by 2? Rf by 2 is a new constant, and guess what constant it is? It is called specific heat capacity at constant volume. I'll come to it in a bit, but it is Cv, and T remains as T only. So very, very interesting result which we have got over here. Let me just block this off for all of you. This is over here. Let me put it. where CV is specific heat capacity at constant volume. In fact, this is molar specific heat capacity, and this CV is taken as F degrees of freedom into R divided by 2. This derivation is not there for you, but I'm just showing this as it is. Degrees of freedom into R by 2 is the molar specific heat capacity at constant volume. That is something which you should remember. No need to derive it. All right. Derivation not required. Okay. Till this point, everything clear? Which also means that if if the temperature if the temperature changes by delta T, the change in the internal energy, the change in internal energy delta U will be given by, think about it, if U is NCVT, what is delta U going to be? N will be there, CV will be there, this will be delta T. So change in the internal energy will be NCV delta T. Also remember one thing, if delta T is positive, that means the temperature increases, then delta U is also positive. But if delta T is negative, that means the temperature will decrease. You will see that internal energy will also be negative. That means it will decrease. But if there is no change in temperature, there will be no change in the internal energy of the gas. Okay, all this is done for ideal gases. Please mind it. So U is NCVT, delta U is NCV delta T. This is absolutely clear. Clear, very good. Dalita, Krishna, Nandu, Bhavna, awesome Disha, very good Sukanya, great Atluru, great, perfecto. Now that we have discussed till here, you will see what is this specific heat capacity and all of that. Let me just put it up. Yeah, it is there on these slides over here. Okay. Now, whenever you supply heat to anything, you heat water or you cool some water, it will become ice, or you heat some stone, it will become hot, or you pass some cold air over marble, it will become cold. So whenever you supply heat, the temperature changes. But if you supply the same heat to different objects, the temperature will not change by the same amount, because what is different for all the objects? Something called as the capacity to absorb the heat. So every object has a capacity, how much heat it will absorb and how much will it reflect in the temperature. So that is why we have something called as the specific heat capacity, and the formula for determining how much the temperature change will be for a heat supplied or absorbed to be Q is given by MC delta T. Very important formula. I'll just block it over here. If Q is the amount of heat supplied, M is the mass of the object, delta T is the change in the temperature, then C is called as the specific heat capacity, which tells me how much heat is required to raise the temperature of 1 unit mass by 1 unit temperature. If I take 1 kg mass and if I change the temperature by 1 Kelvin, how much energy is required? How much heat is required? That is called as specific heat capacity. Formula is MC delta T. Is this clear? What is this specific heat capacity, guys? Everybody till this point, give me a thumbs up. Everybody till this point, give me a thumbs up. Now, the problem is, whenever you discuss gases, you generally don't tell me how much mass of gas is there. Generally, what do you give? Generally, you give the moles of the gas present. And when you give the moles of the gas present, it doesn't make sense to give the calculations in specific heat capacity. which is per gram, per kg, all that. Rather, I will give it per mole, because instead of per unit mass, I will now do the calculations per mole. That is when instead of specific, it becomes molar specific heat capacity. Where is it? Is it there somewhere? Yeah, molar specific heat capacity. This slide should have been here. Okay. Molar specific heat capacity is the amount of heat required to change the temperature by 1 unit for a mole of a substance, not per unit mass, but per a mole of a substance. Okay, I hope this is absolutely clear. Remember, the units for specific heat capacity was joules per kg per Kelvin, something like that. So, if just your specific heat capacity had the units in SI as joules per kg per Kelvin, whereas your molar specific heat capacity has a unit of joules per mole per Kelvin. If I want to do the conversion from here to here, what do I need to do? Just think about it. If I want to go from specific heat to molar specific heat, I need to get rid of kg and get mole over here, and I can multiply by kg on the top. So all I need to do is I need to multiply by kg and divide by mole. So then I will exactly get molar specific heat capacity, isn't it? Kg will cancel and I will get joules per mole per Kelvin. Which means, what are you doing over here? Kg per mole. Kg per mole is molecular mass. That is why you will basically see the molecular mass will be here, and this will be your specific heat capacity, and what you will eventually get is nothing but molar specific heat capacity. You can use capital C or you can use small s. Some books use different symbols. I will use capital C over here. No issues. So this is molar specific heat capacity is specific heat capacity into molar mass. Is this clear, everyone, how this conversion factor comes? Yep. M is the molecular mass of that particular gas. Very, very crucial. Now, there are two types of heat capacities. Two types of heat capacities which you generally will find. If you keep volume constant, then the heat supplied for that n moles, for that change in the temperature, that will be called CV. This is the heat supplied at constant volume. But if the pressure is constant, then the heat supplied at constant pressure will be number of moles into specific heat capacity at constant pressure into delta T. So this is CV and this is CP. If you keep pressure or volume constant, accordingly you get two different things. Accordingly you will get two different specific capacities. So it's very interesting to understand that if you keep pressure constant or volume constant, how much heat it will absorb will also be different. How much change will be there will also be different. That's interesting. And Mayer got a relationship between them. That is why it is called as the Mayer, not the mayor of your city. This is Mayer's relation. And he got this particular thing. Cp minus Cv is the gas constant. A very, very interesting relationship. Cp minus Cv is nothing but R. Also, keep this in mind. Cp by Cv technically equals a ratio called gamma, which is also called as the adiabatic ratio. And this gamma can be proved that it will be 1 plus 2 by degrees of freedom. Again, an important relationship. Gamma is the ratio of the heat capacities, which is nothing but called as adiabatic ratio, which is also 1 plus 2 by F, where F is degrees of freedom. All these relations are very, very important. Okay, all these relations are very, very important. I hope this is clear. Awesome, awesome, great. Now, let's come back to our discussion of, okay, all this was done. Let's come back to a table now. Let's discuss the type of molecule over here in the first place. So first is monoatomic, next is diatomic, or basically polyatomic linear, and next is non-linear polyatomic. Okay, this is the first column. I'll make a very important table for you. Then let's talk about the degrees of freedom, which is small f, degrees of freedom. Monoatomic has 3 translation, 0 rotation, so that makes it 3. Dia or polylinear has 3 translation, 3 rotation, which makes it, sorry, not 3 rotation, 2 rotation, 2 rotational, which makes it 5 degrees of freedom. We have already discussed this right over here. We have already discussed this, how everything has 3, 5, 6, anything. We have discussed this just some time back, which means the next thing will be 3 translation, 3 rotation, which will make it totally 6 degrees of freedom. Okay, awesome. Now we'll have a break after kinetic theory of gases. Now that you have understood till here, let's go to the next thing, which is Cp and Cv ratio and Cv and Cp individual values. If you talk about the value of Cv, specific heat capacity at constant volume, it was Rf by 2. Remember this? Rf divided by 2. Okay. So F is 3. So Cv will be nothing but 3R by 2. This will be nothing but 5R by 2. This will be nothing but 6R by 2, which itself will become 3R. Oh, perfect. Next important thing, let's see what is Cp. But wait a minute, Cp minus Cv was R according to Mayer's relation. So Cp will be R plus Cv. So take Cv and put R to it, you will get Cp value. So plus R if you do, 3 plus 2, LCM if you take, so 3R by 2 plus R, what will you get, my dear students? 2 plus 3 is 5, so this will be 5R by 2. If you add plus R, 5 plus 2 will become 7. So this will become 7R by 2. 3R plus R, this will just become 4R. So that is what your Cp value will be. Last thing will be gamma, which is the ratio of Cp by Cv, which is the ratio of Cp divided by Cv. If you divide this with this, R, 2 will cancel. I'll be left with 5 by 3, right? Which is nothing but 1.67. If you divide this with this, you will get 7 by 5, which is nothing but 1 by 1.4. If you divide this with this, you will get 4 by 3, which is nothing but 1.33. So you can see as the degrees of freedom increase, the value of gamma will come very close to 1. From 1.67, it came to 1.4, came down to 1.33. If I make it 10, 20, 100 degrees of freedom, this value will come very close to 1. So that's what will happen. Okay, so this is a very important table, very important chart for all of you. And I'm pretty sure you can make this chart. You can also draw molecules over here. You can also give the examples which I have given over here just to make this chart more and more comprehensive and more readable. That is how you create your own notes. Okay, you can use my notes also. The PDF will be available in the Telegram channel. So when you are watching this video, right, please we'll share the link also in the description box. Also we'll add it. So just go to the description box. You will be able to find our uh, Telegram channel link, everything is there right over here. Okay. And also let me remind you that our NEET batches are on sale along with the books, along with the flashcards, everything. And this sale is only there till 5th January. So if you're watching this video before 5th Jan, make the best use of the offers which are given to you as a New Year sale. Okay. All our NEET Express batch, the PYQ books, the test series, all India level, the flashcards, everything is on discount. And this is the best time I think you should be buying these things because you are getting that price benefit right now. Okay, great. Let's see how do we solve some questions based out of this. Let's solve some questions. Example, find the internal energy of 5 moles of N2 gas at 300 Kelvin. This is the question. Let's try to solve this. 5 moles of nitrogen gas at 300 Kelvin. Is there a formula directly that we have? Definitely. NCVT. Is the number of moles given? Yes, definitely. 5. Is the value of CV given? Not directly, but I have to think. It's a nitrogen gas, which means it is diatomic. Diatomic gas has 5 degrees of freedom. So the CV value will be RF by 2. So the CV value will be nothing but 5R divided by 2. Temperature already mentioned as 300 Kelvin. So let's put it over here. Cool. 300 by 2 is nothing but 150. So this will become 150 over here. 5 5s are 25. 25 into 15, right? 25 to 15, my dear warriors. How much is it going to be? Come on. 25 multiplied by 15. Come on, my dear students. Yes. How much will it be? Come on. Tell me. Yes, CV value, Krishna, correct. 5R by 2. And that 1 0 will also be there. This R will be there. I think this will be 375. Just check this out. 3750 R. Just check this. 375. 375 R. So you can leave it over here. If you want, you can substitute the value of R also. Perfect. That's how you do this question. Great. Let's move to the next question. If 4 grams of hydrogen is heated by 10 degrees Celsius, find the change in its internal energy. Okay, think about it. How are we going to do this? Find the change in its internal energy. That means you have to find delta U. The formula is NCV delta T. Let's think slowly what each of these values are. Now, change in temperature, whether it is in Celsius or in Kelvin, it is the same thing. So 10 degrees Celsius change is the same as 10 Kelvin of change. Okay. What about CV? H2 gas is obviously diatomic gas. That means it has 5 degrees of freedom. That means the value of CV 5R by 2. Okay. What about the number of moles? Well, the mass of the gas given is 4 grams. Mass of the gas given is 4 grams. But per mole, how many grams should be there? 1 plus 1, 2 grams. So basically, it is nothing but 2 moles of the gas. So therefore, the value of N should be 2, CV should be 5R by 2, and temperature change should be basically 10. 2 cancels. 5 into 10 is 50. So 50R is the value of delta U. So 50R is the value of delta U. Is that clear? Yes, Nandu, who else will answer? And who else will make the question? So obviously I'll only make the question, I'll only answer, right? Because that's how it should be. just like how it is done in offline, right? All right. Next question. Next question. This is a question on the mixture of gases. This often comes many times. Now, let me see if you can think on the spot. If 2 moles of helium is mixed with 4 moles hydrogen, then the Cp, Cv, and gamma of the mixture is how much? These mixture based questions do come very often, and whenever you get mixture based questions, let me remind you what you should be doing. Let me take this slide slightly over here. Yeah, so whenever you get mixture based questions, remember this. First, usually find Cv, it's easier. Number of moles into Cv of the first gas plus number of moles into Cv of the second gas upon the total moles, which is N1 plus N2. Same thing, Cp, this is of the mixture, will be N1 Cp1 plus number of moles into Cp of the other gas upon the total moles. Be very careful with the gamma of the mixture. Don't do N1 gamma 1, N2 gamma 2 by N1 plus N2. That is wrong. Instead, do Cp of the mixture upon Cv of the mixture. This is very, very important. Please remember, this is not the same as N1 gamma 1 plus N2 gamma 2 by N1 plus N2. This is wrong. Please understand that. So I'm mentioning it explicitly. Never ever do this. So let's start with the basics then. Let's find Cv first. So Cv of the mixture will be, okay, helium is nothing but monoatomic gas. Monoatomic gas has how many degrees of freedom? 3. So 3 degrees of freedom. Hydrogen is a diatomic gas. It has 5 degrees of freedom. Keep that in mind. So number of moles 2. Degrees of freedom was 3. So it will be 3R by 2 plus number of moles 4. Degrees of freedom was 5. So 5R by 2. Whole thing divided by 2 plus 4. What do we get? 2 cancels, 4 and 2 cancels. Here we'll get 3R. 4 by 2 is 2, 2 5s are 10. Divided by 2 plus 4 is 6. 10 plus 3, 13. So 13 by 6 R is the Cv of that mixture. That is the Cv of the mixture. Everyone find till this point? Great. Similarly, let's find Cp of the mixture. Not that difficult. 2 into something plus 4 into something upon 2 plus 4, N1 plus N2. If Cv is 3R by 2, Cp will be plus R. So it will become 5R by 2 for monoatomic. If Cv itself is 5R by 2, Cp will be plus R. That means it will be 7R by 2. Very easy to remember. Cp minus Cv is R. Okay. So what do we get next? 2 cancels. So it will become 5R. 4 by 2 is 2. 2 sevens are 14. So 14R. Whole thing divided by 6. 14 plus 5, 19. So 19 by 6 times of R is the Cp of the mixture. Lastly, we'll find gamma, which is Cp by Cv. So 19R by 6 and 13R by 6. R cancels, 6 cancels. It will be 19 by 13. This is for the mixture again. This is how you solve those mixture based questions. This is how you solve the mixture based questions. Is this clear? Everyone? Very good. Awesome. Next question. If Cp and Cv are specific heat capacities for oxygen gas, then Cp minus Cv is equal to question mark. Now, this question might look very strange or very obvious to you. You'll be like, sir, what is this? Is this even a question? I mean, like, isn't it going to be R? But then you have to read the question again. Cp and Cv are specific heat capacities for oxygen gas. You'll be like, okay, what is strange in this? Is it got something to do with oxygen gas? Not yet, but main crux of the problem is it's mentioned specific heat capacity, not molar specific heat capacity. Oh, so what difference does that make? I think I mentioned it over here. Molar specific heat capacity is C into M. This is very, very important. Molar specific heat capacity is C into M, and it is this difference of CPCV, which is all molar specific heat. These are all molar specific heat capacities whose difference is R. Okay, fair enough. So coming back. Oh, so molar specific is C into M. Keep this in mind. Coming back over here, we know molar specific, capital C over here. This is R. This is molar specific heat capacities. And molar specific heat capacity is nothing but specific heat capacity multiplied by molar mass. So what you do, put small Cp multiplied by M, put small Cv multiplied by M. This is equal to R. Perfect. So Cp minus Cv is equal to R divided by M. Now for an oxygen gas, the molar mass is nothing but 32. It is a diatomic gas, so 32. So this will be divided by 32. That's it. Is this clear? Understood? Awesome. Awesome. Yes, the time is 10. So what? Clear? So we have done lot of questions on specific heat capacities, degrees of freedom, and all of these things. So even the chart we made. So I hope this part is clear, because after this, now we'll be doing the thermodynamics part. Okay. So I'll see you in a bit. We'll start with heat, temperature, and thermodynamics in a bit. All right. We'll take a small break. Meanwhile, make sure that you are liking the video and subscribing. Okay. We'll take a small break and return. Hello, hello, hello. Welcome back, welcome back, welcome back, my dear warriors. Yes, so hopefully you had your small little break, and I'm hoping that you had your dinner a long time back because, yeah, this break definitely not enough for dinner. And it's time to continue, get all the kids back into the classroom. Capto is back, Captain Shreyas sir is back over here. Yes, hi Krishna, hi Nandu, hi Tharnal, welcome back, welcome back. I hope you guys are doing fabulous. And well, you know what? After this session is over, I wanted from you, do you want me to do problem solving classes? And obviously put it up in the comments. And which chapter or unit, like electromagnetism or thermal physics or mechanics or kinematics, which problem solving session do you want me to do first? Let's start with that. Okay. Yep. Welcome back, everyone. Welcome back. So, time to begin the class. And we have done kinetic theory of gases, specific heat capacity, degrees of freedom, log equipartition of energy, mean free path, all of this before the break. Uh, Now it's time to move ahead to thermodynamics, which is basically that part where you study the heat, the work, the internal energy, the processes, and the relationships, and all of these things. And we have the three different laws of thermodynamics, which is there in the NEET syllabus. Mainly 90% of the questions will come from the first law, not even zeroth law, not even the second law. 90% of the times, 90% of the questions are generally from the first law. All right. Yes, we will come to practice sessions also, Krishna. Yeah, dinner, I had it before 8 o'clock because I knew that the break will be small. I can't have my dinner at 10 or 11 o'clock. Okay. So, first of all, let's understand some basic concepts of system, surroundings, different types of systems, thermodynamic variables, state function, path functions, and all of that. See, let me show it to you over here. This is a system. It's a system of gas. Maybe you have a container or maybe a bottle. This is a system and water is there in it. Water is a part of that system. Whatever is there around it, like the room, the lights, everything is the surrounding. Same thing over here. This is inside the system. Surrounding is what is outside of it. Right now, this is a closed system because nothing can go out, nothing can come inside. But the moment I open this, it is now an open system. Things can be exchanged, matter, heat, whatever. I hope this is clear. Then, if I do this, obviously now it becomes a closed system. This much is clear, everyone. Thermodynamic system, surroundings, closed and open. Next important thing, which you need to understand, there is something called as isolated system also. What is this difference between closed system and isolated system? Closed means you're just closing the lid, but when you close the lid, maybe the lid is made of metal or some conducting material. So through that lid, heat can exchange, energy can flow. So just because a system is closed does not mean that energy can't move. Matter will not move, but energy can still move. But imagine it is made of wool, thermocol, insulating material like rubber. Then even the energy can't flow. Such a system is then called as an isolated system. Got the difference between them? Isolated and closed system. These are the main differences. Then you have other variables also. Let me come to that. You have something called as the state variables. The state variables which depend only on the current situation, depend on the current condition, and the examples of that are pressure, volume, temperature, entropy, or internal energy, all of this. The next is basically called as path variables, which means how you went there matters. That means they depend depend on the path or the process that you are undergoing. Examples are something like your what do you say, work, or even heat. Heat, the symbol is Q, work done is also W. So how you are doing that process decides how much heat is absorbed, how much work is done, and all these things. I hope this is clear. Okay, now that these things are clear in your head, the next thing is, do we know the formulas, the sign convention of all these things? I think we know for heat at least and internal energy. First of all, let me put it up over here. When you put heat, symbol being Q, Q is given by mc delta T. Usually use this formula for solids and liquids. Solids and liquids. But whenever you have to use gases, heat is written down as Nc delta T. This C is nothing but your molar specific heat capacity. Please mind that. This is just your specific heat capacity, not molar specific heat capacity. Okay, and this M over here is mass. This N over here is the number of moles. Now, depending on the process, you have different heat capacities. So C for the process decides how much heat is absorbed or released for that particular process. Like you have Cp, Cv, etc. So accordingly, you will have different values of C, and accordingly different values of Q. Is that clear? Now, if Q is positive, what does it mean? It means that heat has been absorbed by the system. It is absorbed by the system. Example, when you boil the water, Q is positive for the water because it has absorbed that heat and it is vaporizing. I am heating some food in the microwave. That food Q value will be positive. But when the value of Q is negative, that means the heat has been released by the system. It has been released by the system. That is the sign convention. Is this absolutely clear, my dear warriors? Yeah. If I cool something, the system will lose energy. A hot cup of tea, Q value will be negative because to the surroundings, it will slowly lose that energy and that heat. What about U? U we have already spoken about over here. Delta U, change in internal energy, which is when temperature increases, delta U is positive. When temperature decreases, delta U is negative. We have already spoken about the changes of internal energy, which is going to be useful in our thermodynamics classroom. Okay, coming back over here then. Next important thing is work done. Work. In thermodynamics, the work is always done by the system. Work done by the system. That is very important. Okay. And the formula for that particular work done is just like you have integration FdX. In thermodynamics, it is integration of pressure with respect to the changes in the volume. This is very important relationship again. Let me just block this for you. Work done is integral P dV, integration of P dV, which also tells me that if I show a graph of pressure versus volume, and let's say the graph goes like this. Remember, the graph can never be below or on this side because pressure and volume can never be negative. If this is the start, this is the end, this is the initial, this is the final. Let's say sometimes this could be the graph. where this is the initial state, this is the final state. Integration always means area under the graph. So if, for example, you find the area under this particular graph, which is this one right over here, okay? So this one right over here. This particular area is considered positive because it is expansion. It is expansion. The final volume is higher than the initial volume. The work done will be considered as positive. Whereas over here, if you take the area under the graph, that's what integration is all about. It is always the area under the graph. Initially, the volume is much higher. Finally, the volume is much lesser. This work done is negative under compression. So this is the sign convention for work done. Very, very important. Is this absolutely clear, my dear warriors? Understood till this point? Perfect. Now, imagine something called as a cyclic process. Imagine something called as a cyclic process. What is a cyclic process? In a cyclic process, you return back to the initial state. Initial state. Not necessarily via the same route or same process, maybe via a different route or a different process. So just to show you an example of cyclic process, let's say this is a graph of pressure and temperature, or let's say this is temperature, this is volume. A cyclic process could be something like this. That's it. This is a cyclic process. You started from here and you have come back to the original state. This is a cyclic process. Okay. So you complete a loop. It will be like a loop that is called as a cyclic process. Whether it is volume temperature, pressure volume, density pressure, whatever it is, you should come back to the original state. That is a cyclic process. Now, the interesting thing about cyclic process is this. Imagine you have been given pressure volume graph. Imagine you have been given the pressure versus volume graph. And let's say the graph looks something like this. You have completed one cycle and you have come back to the original state, or let's say like this. You started from here, you continued your journey and you came back to the original state like this. In each of these cases, what you will see, because you returned back to the original state, the delta U will always be 0 since delta T is 0. So there is no change in the internal energy. No change in internal energy for the entire cycle. For the entire cycle, the energy comes back to its original state. So delta U is always 0. Keep this in mind. But what you will notice is the work done will not be 0. In fact, if you calculate this particular area, which is there within this particular loop, this area is positive for clockwise. So this is considered as positive work done. Positive work because it is clockwise. The moment you go in an anti-clockwise cycle, the moment you go into an anti-clockwise cycle, that area considered as negative work done, and this is for anti-clock. Anti-clock. Is this clear? So negative work for anti-clockwise pressure volume graph, positive work for clockwise pressure versus volume graph. Positive means, the system is doing work. Negative work means the work is done on the system. I hope this is clear. Yes, I hope this is okay. So whenever it is compression, the work is done on the system. Work done on the system. When it is positive, it is following the definition. So work done by the system. Keep this in mind. Okay. Fair enough, guys. Understood. Cyclic process, work done, positive, negative, etc. Till this point, absolutely clear. Okay, fine. All these definitions, everything, I have kept it here also. Not an issue. Temperature, heat, Q, we have discussed this anyways. Uh, Now, there is one important thing which you should be aware of. There is one important thing which you should be aware of. Conversion of joules, that is your heat, um, from one unit to another, that is like calories. And that conversion factor is called as the mechanical equivalent. And that standard value is, if you take 1 calorie is 4.2 joules of basically heat. So keep this in mind. So 1 calorie is basically actually 4.18, but you can approximate it to be 4.2 joules. Now, what is the significance of this? Hundreds of years back, people did not know heat and work are actually two physical quantities but of the same units. Like, imagine some person in England was measuring length in feet and some person somewhere else was measuring length in meter. Like, I'm also measuring length. I'm also measuring length. Like, it's 2 feet. Some person says, no, it is, hardly zero point 0.7 meters, something like that. So actually, both are measuring length, but in different units. So same thing was about energy and work. People thought energy is a different quantity, work is a different quantity, until James, Clark and all these people, James Watt, he told that actually heat can be converted into work, work can be converted into heat. They are interchangeable, interconvertible, and the conversion factor was 4.2. So here calories was usually used for heat and joules was usually used for work, and this is that conversion factor. That is why it had significance. Heat and work can be converted into each other. What is 1 calorie? Calorie is the amount of heat required to raise 1 gram of water by 1 Celsius. That was what 1 calorie was defined as. And what was 1 joule? 1 joule is the amount of work done when you apply 1 Newton force and displace it by 1 meter. Got it? So that's the conversion factor. Okay. Now let's come to the laws of thermodynamics. There are two laws which we study in the start. And the first law is the zeroth law. The next law is the first law. You'll be like, why the hell did you say zeroth? You can just say this is first, this is second, just like Newton's first, second law. But the problem is first law came first, zeroth law came later, because already the law which was given here was popular. That's why this law which came later, people did not want to confuse the audience saying this is the first law, now this will be called second law, because this was used for a longer time. So for historical reasons, they had to name it a number lesser than first, and it was more fundamental. That's why they called it zeroth law. If tomorrow somebody comes with another more fundamental law in thermodynamics, then that will be called as the negative 1th law, because I don't want to change the names of these two, because now it is popular, it is widely known what is zeroth law, what is first law. Okay, coming, what is zeroth law? Zeroth law is when two things are in equilibrium with the third thing, then the two things are also in equilibrium with each other. What does that mean? Let's understand that. Let's understand that. See, for example, okay. Now, what do you mean by, first of all, thermal equilibrium? What do you mean by thermal equilibrium? Let's define that first. So, the meaning of the word thermal equilibrium. What is the meaning of the word thermal equilibrium? Is when there is no net heat exchanged, there is no net heat exchanged between the bodies, and their temperatures are same, and their temperatures are going to be the same. And this is a known fact that if I have something which is very hot versus something which is, let's say, cold, we know that the heat always goes from the hot body to the cold body. Heat will always flow from the hot body to the cold body. But if there are two things, if there are two things which are equally hot or equally cold, same temperature, then you will see that there is no heat flow. Then there is no heat flow, and such two bodies are said to be in their thermal equilibrium. Is this absolutely clear? So this first diagram versus the second diagram. They are not in thermal equilibrium. These two bodies are definitely in thermal equilibrium with each other. Now, what the zeroth law says, if two things are in equilibrium with third, then they two are also in equilibrium with each other. Meaning, for example, if temperature of A is equal to and temperature of B is equal to temperature of C, A is equilibrium with C, B is also in equilibrium with C, then you can say that temperature of A is also equal to temperature of B. That is what it says. Simple example, guys. Okay, if A is equal to C and B is equal to C, then A is also equal to B. Is that clear, everyone? Understood? The best application of this is, imagine there is a Pandu. Imagine there is a Pandu who has fever. Imagine there is a Pandu who has fever. So he goes to the doctor. Doctor says, I'll have to measure your temperature. He's like, okay, fine, measure the temperature. So he puts the thermometer. What does the doctor do? He puts the thermometer. So the bulb of the thermometer is here. So this is the thermometer which has been put, okay, under the arm to measure the temperature. Then the mercury inside the thermometer, it will start rising. If it shows like 100, 101, the doctor will understand, okay, he has this much fever, I have to treat him. This application is actually of zeroth law. How? I will tell you. Mercury is not touching the Pandu. Pandu is only touching the glass. Glass is touching the mercury. So when the thermometer mercury level adjusts itself and stabilizes, that means no more heat flow processes are going. That means thermal equilibrium has been achieved. That means all the three bodies are in equilibrium thermally. So all the three things are at the same temperature. Who are these three things? Pandu, glass, and mercury. So Pandu is body A, who is in equilibrium with the glass. The mercury is the body B, which is in equilibrium with the glass, which is body C. And because both of them are independently in equilibrium with the glass, hence Pandu's temperature must be equal to the mercury's temperature. So when you measure a sick person's temperature by placing a thermometer, you are actually measuring the temperature of the mercury. But because of zeroth law, I know the mercury's temperature will be the same as the Pandu's temperature. Got it? The significance of this? Not many people know this. Everybody till this point absolutely clear? Let me know. Then we'll go ahead. Great. Perfect. This is your zeroth law of thermodynamics. Now, what is the first law of thermodynamics? Again, we'll take use of Pandu, guys. And this is very simple. Imagine if a Pandu, he was sick in the zeroth law, right? He's sick, he's very weak. If you give him energy, basically, let's say he drinks some, uh, energy drink or some ORS or some, Glucon D, something like that. So this is an energy drink. It has some calories. It has some calories in it. So this is some kind of some energy drink. He drinks that, and because of that, what happens is this Pandu feels much better, and he's more happy, and he has gained some energy. Probably he will start, lifting things. He will start doing work. So this is exactly the first law. Here, our Pandu is our system. Pandu is our system. This energy drink was containing some calories. That means it was like heat. So basically, what it says is that whatever heat is absorbed by the system, whatever heat is absorbed by the system goes into goes into what? Number one, the system has become more stronger. That means internal energy in basically changing changing the internal energy, and at the same time you are doing some work. You are able to lift things. You are able to do some work. So basically, also for doing work. Also for doing work. So this is exactly the first law. So delta U plus W is equal to Q. Very, very important. Very, very important. This is the first law of thermodynamics. Now, if that is the first law of thermodynamics, if I go back to the cyclic process definition, delta U is zero. Delta U is zero, and we know first law, what does it say? Q is equal to delta U plus W. Delta U is zero, that means Q will be the work done. So you will always see in such cyclic processes, whatever Q is there, it will be the complete work for the complete cycle. Because this is zero. Delta U is zero. Q, heat which is absorbed, will be completely utilized for doing work. Okay, absolutely clear on this? Great. Just give me 1 minute. I'll just take a small break and come. Just hold on, yes. Just hold on 1 second. I'll just take a 3 minute break and come. 3-5 minutes break. Just give me 1 second. Brief interruption. Let's get back. Yeah, so Q is basically delta U plus W. That was our first law, and we discussed about how in the cyclic process, because delta U is 0, Q exactly equals work done. Okay, so let's take up some examples on it. I have kept some questions. One second. Hmm. Okay, let's see if we can do this. For the indicator diagrams, basically pressure volume diagrams below, which of the following is not correct? Okay, not correct. Be careful. The cycle number 2 is a heat cycle. Net work is done on the gas in cycle 1. Work done in cycle 1 is positive. Work done in cycle 2 is positive. This is pressure volume graph. As you can see, whenever it goes clockwise, the work will be positive. So work done is positive for cycle 2, yes. Whereas over here, it is anti-clockwise. So the work done will be negative. So work done is positive for cycle 1. Obviously, C is wrong. Net work is done on the gas in the cycle, because work is done negative. That means it is done on the gas. It is done on the gas. So option B is correct. Cycle 2 is a heat engine cycle. Basically, think about it. Work done is positive. That means even Q is positive. That means heat has been absorbed and work is done by the gas. And that is what engines do in your cars, bikes, everything. Engines, they burn the fuel. So they will absorb that energy which is being developed by the combustion, by the burning of the fuel. And they end up doing work. So cycle number 2 is of a engine. Correct. So the only statement which is wrong is option C, which is C for Captain Shreyas. Perfect. That is the answer. Hello, Spandana. Welcome aboard. Yep. Everybody with me on this? Understood? Oh, clear? Oh, shall we go ahead? Okay, let's do one more question. Let's see if you guys can do this. There is a gas which goes from state A to state B via 3 different paths: path 1, path 2, and path 3. Question is, if you compare their work, whose work is more, whose work is less? Okay, let's try to do this. We all know that whenever you have to calculate work is always calculated by graphical methods, by finding the area under the pressure volume graph, pressure versus volume graph. So just look at the area quickly, you will understand it. It is not a big deal at all. I mean, if you see the first area, that is for graph number 1, it is only this much. It is only this much. So the work done is only the area of this much part, which I have shaded. If you look at the second graph, the area is a little bit more. As you can see, it is this much. Yes. So slightly more. So the second graph has more area. That means more work done in the second process. If you look at the third graph, that has even more area. That extra part is there, as you can see. So the third graph having more area will do even more work, guys, as you can see. So that's it. That is the answer then. Work number 3 more than work number 2, more than work number 1, which is option B. B for biology, B for Baswa sir. Correct. Kamali Atluru Krishna, perfecto. Awesome answers by all of you. Okay. Yeah, these are the questions which I had over there. All right. Now, hold on. Let's do some questions over here. Let's do some questions over here on the first law. If a gas is heated by supplying supplying 20 joules of heat and 40 joules of work is done on it, then delta U is how much? Then the change in the internal energy is basically how much? That is the question. Let's try to understand. Heat is given, internal energy change is asked, work done is also given. So obvious question of first law of thermodynamics. Okay, so let's try to do this. Since the heat is being absorbed, so I will put Q as plus 20. The plus is coming because it has absorbed the energy, absorbed the heat. Next is about the work done. The work done is 40, but be careful, the work is done on it. What is it referring to? On the gas. Whenever work is done by the gas, it is positive. Whenever work is done on the gas, in physics, not in chemistry, in chemistry it's opposite, then it is negative. Work is done on the gas. This is work done on the gas is considered negative. And we all know the first law of thermodynamics, Q is delta U plus W. Q is 20. Delta U I do not know. Work done is negative 40. So therefore, our delta U will be 20 minus 40 goes there as plus 40. Therefore, the change in the internal energy will be 60 joules. Many people forget the negative sign here, or they think work is 40 and they will get a completely wrong answer. Got it? So be careful about the sign convention, or else things can go very south, meaning very bad. Okay, perfect. Moving on to the next question. Moving on to the next question. When ice melts into water at 0 degrees Celsius, delta U, work and heat, what are their signs? What are their signs? That is the question. Is it 0? Is it negative? Is it positive? That is the question. It's a beautiful question. Many people again make a lot of mistakes. It's very silly mistakes over here. What are the signs for all of them? Let's understand it. First of all, just imagine you had a block of ice and then you convert it into water. Ice has lesser density, water has more density, and we know this by a fact because ice floats on water. So ice is less dense, water is more dense. Okay, so that means this should be basically our water. This is basically our water. It is more dense, and this is basically our ice. Basically, it is less dense. It is less dense, so it will occupy more space around it. Okay. Now, maybe more for half an hour, 45 minutes at Luru, not more. In this process, when ice is going to melt into water, ice is going to melt into water, you will have to heat it. And because you are going to heat it, what will be the sign of the heat? It will be positive because heat has been supplied. You have to heat it. It will absorb. It will basically absorb that heat which it has been given, and that's how it will melt. Obvious? Everybody clear? What about the work? Well, ice was bigger because ice has less density. Ice has less density, and we know this because it floats. It has compressed, and because this process was of compression, what should happen when volume goes smaller? The work done is negative in case of compression. In case of compression, contraction, it is negative. In expansion, work done is positive. Okay. What about delta U? Lot of people are going to make a mistake here and they are going to say, sir, over here, I know because ice converted into water at 0 degrees Celsius, the temperature was constant. So delta T was 0 and delta U being NCV delta T. So delta U is also 0. By this logic, delta U should be 0, but this doesn't make sense at all. Because think about it, logically speaking, delta U plus work should be this. So if at all I put this as 0, how can be 0 plus a negative number be a positive number? So first law becomes invalid then. So there is something wrong because first law should always be true in thermodynamics. So that means whatever I have written down over here is slightly wrong. So understand, this is a wrong analogy, wrong idea. This is not correct. This cannot be it cannot be used. It cannot it cannot be used. Reason being, ice to water, none of them are gases. This formula is only for gas, and that too only for ideal gas. This is not even a gas. So you cannot use this. Number one. Number two, realize this, that when ice goes into water, yes, the kinetic energy remains the same, but there are bonds which are broken. So internal energy increases because bonds are broken. Bonds are going to be broken. So because of which the internal energy gets affected and the internal energy will actually end up increasing. Understood? Why the internal energy increases? It is the sum of kinetic energy and the potential energy. Kinetic energy did not change because temperature was same, but the potential energy increased, because of which internal energy increased. And that is the reason why this will be positive in nature. So you cannot use this formula because it's only for ideal gas. It's solid to liquid. That's why you have to think more deep. That's why concepts are important. If you just remember formulas, you will never get it. Sign convention in physics and chemistry is confusing. I would recommend either remember physics or remember chemistry. And this is true every time any confusion happens. Like for example, range up the plane, range down the plane, inclined plane, something like that. If you always get confused, never remember both things. Always remember one thing, and you know the other thing is exactly opposite. So on the paper, in the rough work, always start with what you know and then just quickly change the signs. Understood? So that is a easier way to do this because you'll again get confused. Was it plus or was it minus? Always remember one thing then, completely one thing, because you know other thing is exactly opposite. Okay. So yeah, that were some questions of first law, some crazy questions. Now let's go to the last part of this, which is processes, and then the second law. Second law is not much. See, there are two kinds of processes that we usually see in our physics, but usually we do not go to irreversible processes. We go to reversible processes. So what is the meaning of this reversible and irreversible process? They're exactly what they sound like. Reversible process is where you can go in both the ways and you will pass through the same situation while coming back. Meaning, example, say, you are going to your school. You are going to your school, and from your house, you take a particular route. You decide, okay, I forgot something. So you come back from the school. You take the same road. That is a reversible process. But imagine in a city like Bangalore, okay, if I decide, if a student decides to go to school and try to come back by the same way, not possible. If you are from Bengaluru or some big city like, I don't know, Chennai or Mumbai, Delhi, Hyderabad, all right, because they have one ways. If you go from one route, the coming back route is completely different. You have to go from some other area only. The going and coming paths are not same. And you might encounter different times, you might encounter different things on the way. So that becomes like an irreversible process. That's a very vague example, but I hope you got it. Sarji, then Q should be equal to negative in the previous question. No. Uh, this positiveness is more than the negativeness. That is why this is positive. Imagine this is plus 5, this is minus 2, this will be plus 3. So this is more positive, this is less positive, this is less negative. Think of it like that. Okay. So reversible processes where, every time in every step, you know what the state is, you know what the situation is, you know what the pressure, volume, temperature, entropy, internal energy are. That means at every step, you are going with caution, you are taking small steps, and you are allowing things to settle down. You are seeing, okay, pressure, volume, temperature, entropy, internal energy. Okay, next step, slowly you are going. So it's a slow process. So usually very slow step processes where you allow things to settle down and then take a next small step, they are reversible processes. But sudden processes, or where things don't settle down, those are then going to be irreversible processes. Like most of the processes around us are irreversible, because it's not like when you turn on the AC, AC will be like, okay, wait, oh, the temperature has come down by 0.1. Okay, wait, now I will reduce the temperature by 0.01. Next by point. No, AC like bomb, it will throw that air onto your face. Immediately the temperature will drop. So that is all irreversible process. A tire bursts, suddenly the pressure changes. All the processes around us are irreversible. It is a realistic process, whereas reversible is a more idealistic process. But in our NEET physics, we study reversible because you have to start somewhere, obviously, number one. Number two, you can come very close to the reversible values by making the processes a little bit slower. That's all. And reducing friction, applying lubrication, all these things, you can make it a little bit more idealistic. Okay. So like melting of ice, evaporation of water, it happens slowly. So they are more or less reversible processes. Great. Is this point clear? Now, we study mainly four different processes and then a general process called as a polytropic process. I'll come to that. The four processes that you study are isothermal, number one, adiabatic, isobaric, and isochoric. As simple as that. In each of the processes, one or the other thing is constant. For example, in isothermal, temperature, thermal temperature is constant. Adiabatic, no temperature exchange happens, sorry, heat exchange happens. So heat absorbed or released is zero. Isobaric, bar is a unit of pressure. Isobar means same pressure. Pressure is constant. Isochoric, that is where the container is contained. Nothing expands or contracts. That means volume is constant. These are the four basic processes that you generally study. And in each of these processes, we can write down all the things which happen in a very beautiful small table that I can make. Let's say we start with the process over here. First is iso. Let's start with isobaric first, then isochoric, then isothermal, and then adiabatic. Okay, let's write down everything. This table will be very helpful for you. You can download this entire PDF after the class is over. Remember that. Okay. What is constant in every one single process? Let's write that down also. In each one of them, what is constant? It is the in isobaric, it is the pressure which is constant. Here it is the volume which is constant. Here it is the temperature which is constant. And here heat is basically zero, or rather you will see it is the pressure into volume raised to gamma which is constant. Because pressure is constant, you will see volume by temperature, PV is nRT, right? Volume by temperature will be constant. When volume is constant, pressure by temperature will be constant. And when temperature is constant, pressure into volume will be constant. So when pressure is constant, volume is proportional to temperature. When volume is constant, pressure is proportional to temperature. When temperature is constant, PV is nRT. Pressure will be inversely proportional to volume. Here, in adiabatic process, PV raised to gamma is a constant. These are the fundamental things. Next important thing which you should know. Let's write down our equation. Q is delta U plus the work done. Who and all values, which are all values do I know? I think adiabatic, it is very obvious that Q will be obviously 0. Q will be obviously 0. So 0 will be delta U plus work. Then if you talk about isobaric, everything will be there. So Q will be nothing but NCP delta T. Delta U will be nothing but NCV delta T. Work, instead of integration, because pressure is constant, it will be P delta V. Got it? Q is this, delta U is standard formula, work will be P delta V, no need of integration required. In isochoric process, volume is constant, no change in volume, so work done will be 0. Work done will be 0. And delta U will be just NCV delta T as usual. Heat will also be NCV delta T. So NCV delta T is NCV delta T plus 0. Work done will be 0. Is this absolutely clear, my dear students? Okay. Next, for isothermal, delta U will be 0 because delta U is NCV delta T. No change in temperature. So this will be 0. What about the work done? The work done will be nRT log of volume 2 by volume 1. This is very, very crucial. So therefore, the heat which is there will be nRT log V2 by V1. Okay, the heat which will be absorbed or supplied will be nRT log V2 by V1. This comes by integration. You can also write this as nRT instead of V2 by V1. You can write it as log P1 by P2 because pressure into volume is constant. So P1 V1 is P2 V2. So P1 by P2 will be V2 by V2, inversely related to each other. Okay, Warrior Pandu whistle podu. Yes. Okay, perfect. Is this table absolutely clear in everybody's head? You should remember this. Who and all is constant, who and all is 0, who and all values for which single process. Basically, delta U is always NCV delta T. In the case of isothermal, no delta T, so that's why no internal energy change. In isochoric, no work done because no contraction, no compression. In adiabatic, no heat, so Q itself is absolutely going to be 0. Is that okay? Only isobaric has all the three terms, P delta V, this and this. Everything is there. Okay. Now, let me talk about something called as the next process over here. Only I will write down. Free expansion. Free expansion. Free expansion means you take a gas and just leave it in vacuum. It's going to expand permanently. There is no stop to it. There is nothing which can stop it. Such a process, I mean, what will happen? It will not be able to exchange heat with anything. It will not have any change in the internal energy. It has nothing to do work on. So 0 will be 0 plus 0. So all these terms are going to be 0. So this is a very unique process where everything just happens to be 0. There is no meaning of discussing pressure or volume or temperature because it is always going to be in a state of permanent expansion. It's free expansion. There is no end to it. So you can only measure pressure, volume, temperature when it stabilizes. When it has not stabilized, there is no sense in measuring the pressure, temperature, etc. There is no boundary to it. Yes, it's a limitless system. So this is the only place where everything happens to be zero. The last type of process is called as a polytropic process. Very few times questions have come on this, but I feel we should discuss this also. A polytropic process is where the the process can be described as some p into v raised to alpha. Alpha is any real number, is basically some constant, where alpha is some real number. It could be root 2, it could be half, it could be -1, -100, 5,000, whatever, some real value it should be. When it is PV raised to alpha is constant, then it is called as a polytropic process. Now, what is so special about polytropic process? Observe this carefully. See, no matter what the process is, always our delta U is going to be NCV delta T. This is for all ideal gas processes. There is no exception only for this. Isothermal, isobaric, adiabatic, anything, always delta U is NCV delta T. This we always knew. Now coming back over here, for adiabatic process, because this was delta U plus W, delta U we know is technically NCV delta T, and this is nothing but W. Okay, coming back. Okay, what about work? What about Q? Let's come to that. The formula for work done, is very, very similar to the work done formula for adiabatic process. Why, you might ask? Observe this. PV raised to gamma, gamma is Cp by Cv. Here, PV raised to alpha. Just mathematically think, it is as good as saying, instead of alpha, I can just put gamma and then look at the formula for work done. What is the formula for work done? NCV delta T. NCV delta T. So if you solve this for adiabatic process, observe this, what you will get. For alpha equals to gamma, basically adiabatic process, meaning PV raised to alpha is PV raised to gamma. The work done plus delta U was 0. Therefore, work done will be negative delta U. Therefore, it will be minus NCV delta T. But what is the value of CV, you might ask? The value of CV is R divided by gamma minus 1. Now, how do you get that? That is not that difficult because we already know this. Cp by Cv is gamma. Therefore, Cp is gamma times of Cv, and Cp minus Cv is R. So instead of Cp, you put gamma times of Cv. This will be R. Therefore, Cv into gamma minus 1 is R. Therefore, Cv is R upon gamma minus 1. So instead of Cv, you can just put R upon gamma minus 1 into delta T. Now just imagine this. The work done came out to be this for a adiabatic process, Nr delta T by gamma minus 1. If you want, you can write it as Nr delta T, Nr delta T upon 1 minus gamma, This is all for adiabatic. But in the adiabatic, the speciality was gamma was alpha. So if you replace gamma with alpha, which was the original substitution, I will get back the work done for in general polytropic process. In general polytropic process, I had started my assumption saying alpha is gamma. What is the work done? The work done is this. So if gamma is replaced back to alpha, I should get back the work done. Hence, the work done formula will be exactly this. It will be nothing but nr delta T upon 1 minus alpha. Got it, guys? How do we get this formula? Everyone? Very, very simple trick to get this formula. No need of complicated arithmetics, calculus, integration, not at all needed. Just replace alpha with gamma and again replace gamma with alpha. That's all. Yeah. So this is the formula. Then the last thing will be, sir, what is the formula for heat, sir? What is the formula for heat? You don't have to remember any formula. Q will be, simply put, just add both of them, delta U plus work done. That's all. Delta U plus work done. Just substitute both of them. You will get the answer to this. Okay. So you just have to add both of them. You will get the total heat which has been absorbed or released by that particular gas. No formula for it. It's just find them out individually. No other way to do it. Okay, great. Hello, Mohammed Abdullah. Welcome aboard. All right. So with this, I think we can start doing some questions on thermodynamic processes. On thermodynamic processes. One more thing is there over here in polytropic process, which I forgot. Let me remind you. If you have a pressure versus volume graph, and let's say PV raised to alpha is constant, meaning this is how the graph is. PV raised to alpha is a constant, pressure versus volume graph. Now, somebody decides that we will draw a tangent to the graph. This is basically a tangent to the graph. That tangent will have some slope. That tangent will have some slope. So the slope of pressure versus volume graph, which will be the slope of the tangent, which will be the slope of this graph, which is dp by dv, dy by dx, rate of change of vertical by horizontal. This will be exactly equal to negative alpha times pressure by volume. Very, very important. This was our tangent. This was our volume. What is P and V over here? It is the value of the pressure and volume at that instant. So whatever pressure was there, whatever volume was there, it's exactly that. So this was your pressure. This was your volume. So the slope of this graph is negative alpha. Alpha is that same alpha over here, P by V. Very, very important. Now, why are we discussing this? Observe now. There is a very interesting story to this. Now, if you discuss isothermal process, when temperature is constant, basically PV is constant. Is it not as good as saying PV raised to 1 is constant? Oh, PV raised to 1. 1 looks like this. 1 looks like this alpha which is there in the polytropic slide. PV raised to alpha. Alpha is basically 1. Oh, so it's a polytropic process where therefore alpha is basically 1. That means the slope of pressure versus volume graph for isothermal process, for an isothermal process will be, check this out, minus alpha P by V. Alpha is 1, so it will be minus pressure by volume. Same thing if you do for adiabatic process. Same thing if you do for adiabatic process where PV raised to gamma is constant. Comparing, you get alpha is gamma. So therefore, the slope of pressure versus volume for adiabatic process, is negative, alpha, replace it with gamma, P by V, which tells me it is minus P by V is there here also. So it is gamma times the slope of isothermal process. So the slope of adiabatic process, is more than isothermal process gamma times. This is a very, very important formula. There could be many questions based out of this, direct questions. In fact, if you see graphically, it will look something like this. This is your pressure, this is your volume. Adiabatic has more slope, steeper than isothermal. So if isothermal was like this, and if you draw a tangent at that point, maybe the tangent goes like that, then you will see the adiabatic graph is steeper. That means it will go probably like this. So if you draw a tangent over there, it will be more steeper. That is how it will be. Is this absolutely clear? Okay, the yellow one is obviously for adiabatic, the orange one is obviously for isothermal. So adiabatic is steeper, isothermal is not as steep as adiabatic at that same point. Okay, no problem, Abdul. I'm so glad you are watching the recorded classes. It doesn't matter whether you watch live recorded. Live is more interactive, fun, and it feels like you are belonging somewhere. You feel you are more regular and no backlogs are there. Recorded is fine if you have some other commitments, classes, or you're a partial dropper, no issues. All right. So these are the critical aspects which you should know regarding the thermodynamic processes. Okay. So let's do some questions, my dear students. The slope of an isotherm for for CO2 is is 10 units, or basically just 10. It's a ratio, so 10. Then the adiabatic slope is how much? That is the question. Let's try to solve this. The adiabatic slope is how much? This is completely based on whatever we just studied. Adiabatic is gamma times more slopier than the isothermal. So the slope of adiabatic is gamma times the slope of the isothermal process. Now, what is gamma? I don't know. Let's come to that. Slope of isotherm is 10. Now, to find out gamma, let's understand what is this CO2. CO2 is a linear polyatomic molecule. And for a linear polyatomic molecule, there are 5 degrees of freedom. Gamma being 1 plus 2 by F, this will be 1 plus 2 by 5. So this will be 5 plus 2 by 5. So this will be 7 by 5. So gamma is basically 7 by 5. So 7 by 5 will come over here. 5 and 10 will cancel off, of course, will become 2. So it will become 7 into 2. So it will become 14. So the adiabatic slope is 14. That's what it is. It is slopier than your isotherm. Okay, very good. Thank you. Thank you for all the love. Oh, okay. Awesome. Awesome. Crystal clear, Atluru. Great, great. Perfecto. Moving on to the next question coming up on your screen. If a helium gas of 4 moles is taken from, wait, at 4 moles, let's say at temperature T and volume V is expanded isobarically to 2V, find Q, delta U and the work done. Find Q, delta U as well as the work done in this particular process. Let's try to do this. Okay, everything we have to find. This is for a helium gas, 4 moles, temperature T, volume V. Okay, let's see which one is the easiest of them all. Okay, I think I don't know yet. It's not so easy to judge. But let's think what might be happening in this entire process. If I say initially the pressure was P, or rather the volume was V, temperature was T, number of moles is going to be constant. The pressure will be nRT by V. N is 4, R is R, T is T by the volume, which is basically V. So pressure is 4 RT by V. That is the initial pressure. If you look at the final value of the things, finally, the volume is made to 2V. What will happen to the temperature? It is clearly mentioned isobarically. That means the pressure can't change. So it will still be 4 RT divided by V. Okay. What about temperature? Well, we all know for an isobaric process, what exactly happens? Because pressure is constant, volume is directly proportional to temperature. So if volume doubles, temperature should also double. So that means the temperature is basically 2 times of T. Temperature is basically 2 times of T. Everybody fine till this point? Clear? Yes? Awesome. Amazing. What next? What next? Let's see which one is the easiest. I think we can go to delta U, and before going to delta U, one small thing, because it is helium gas. So I think we can write down what is the helium gas is a monoatomic gas, and for monoatomic gases there is 3 degrees of freedom. For 3 degrees of freedom, we can just say that the CV value is 3R by 2, CP value is 5R by 2, and the gamma value is the ratio of these two, so 5 by 3. These are the standard things. Okay, so let's start writing down whatever we can now. Starting off with, let's say, delta U. Delta U is NCV delta T. What is number of moles? 4. What is the value of CV? That is 3R by 2. What is the value of delta T? Change in the temperature. So it will be nothing but 2T minus T. So 4 by 2, 2 into 3R. 2T minus T is T. 2 3s are 6. So 6RT will be the value of delta U. Okay, next. What about Q? Q is nothing but NCP delta T. What is moles? 4. What is Cp? 5R by 2. What is delta T? 2T minus T. Okay, so 4 by 2, 2. 5R as it is, 2T minus T is T. 2 5s are 10, so 10 RT is nothing but the value of Q. Okay, next, finding the work done. Well, work done can be done easily. It will be Q minus delta U. That's it, first law. So Q is 10 RT, delta U is nothing but 6 RT. So therefore, it is nothing but going to be 4 RT. So work done is 4 times of RT. That's it. Clear how to solve these questions? Let's do another question coming up on your screen. If a nitrogen gas at 5 kilopascal and 20 meter cube is compressed to 4 meter cube isothermally, then the work done delta U Q is how much? Okay, that is the question. Let's see if we can do this. If anything else is needed on the way, we will add that data as and when required. If there is a gas at 5 kilopascals and 20 meter cube and it is compressed to 4 meter cube isothermally, then what is work delta U and Q? One thing is clear, since it is an isothermal process, be careful. It is clearly mentioned it is isothermal. That means temperature is constant. So therefore, delta T will be 0. Therefore, delta U automatically becomes 0. That is one very easy way to locate delta U. That also means whatever heat is there will be equal to the work done because delta U is absent. So the Q value should be equal to the work done. Okay. So if this is the situation, then just let's find out the work. But to find out the work, the formula goes something like this. The work done formula is nRT log V2 by V1. But I don't know N, I don't know temperature. That will be another headache. But we know one thing, nRT is PV. So either you write it as P1 V1 or P2 V2, it doesn't matter. So P1 V1 log V2 by V1 is also the same as this formula. This is using your gas law, ideal gas equation. nRT is PV. Okay, you can write it as P1 V1 or P2 V2. But anyways, they are equal. Do I know P1 and V1? Yes, I do know. 5 kilopascal. So 5 into 10 to the power 3. Volume 20 meter cube. Log of volume 2 by volume 1. Volume 2 is 4. Volume 1 is 20. Okay. This will become 5 2s are 10. 10 into 10, 100. So this will become 10 to the power 5. Now here, this 4 by 20, I can write it as log 1 by 5, which can be written down as negative 10 raised to 5 ln 5. So that's it. You can leave it like that because when it is down and you bring it on the top, it will become negative power. Yeah, so that's why that negative sign has come outside. So this is the work done in joules. If you want, you can also write it as minus 100 ln 5 kilojoules. But work done will be also Q. Therefore, Q will also be equal to minus 100 log 5 kilojoules. So that is the answer to this question. Is this okay? Everyone clear about this? Perfecto. Okay, shall we go ahead? Let's move to the next question coming up on your screen. Get ready for it. Get ready for it, my dear students. All right. Okay. If a nitrogen gas follows PV raised to 3 is constant process. Find the molar specific heat capacity for that particular process. If there is a gas which obeys this particular equation, then find the molar specific heat capacity. So this is also another common question which can be asked. Now, the moment you see this kind of question, realize this is a question on polytropic process. How do you know that? Because this equation can be easily compared to PV raised to alpha is a constant. That means alpha is basically 3. Oh, so this is a polytropic process. Okay, fair enough. For polytropic process, how do I find molar specific heat capacity? Okay, we'll think about it. But for now, I know one thing. Whatever is that Q should be N and C for that polytropic process into delta T. Somehow, I want to find that C polytropic. For finding that C polytropic, I think I need Q. But how do I find Q? There is only one way. Let me just go back and show that to you. It will make sense. Come back over here. For that polytropic process, where is it? Hmm. For that polytropic process. To find Q, find the delta U, find the work and add them, you will automatically get the value of Q. Oh, so I have to find this and this separately. What is delta U and work done formula? I've written it down over here as it is. Let's use this. As it is, let's use this, my dear warriors. So first of all, delta U. What is delta U? Delta U is NCV delta T. Number of moles not given. CV, it's a nitrogen gas. Okay, let's think about it. For a nitrogen gas, it is a diatomic molecule. Diatomic molecules has 5 degrees of freedom. 5 degrees of freedom. So for 5 degrees of freedom, CV value will be 5R by 2. 5R by 2 into delta T. So that is your delta U. What about work done? Work done formula is nRT. I just gave it over here in case you forgot. See this. Work done. nRT delta T, sorry, by 1 minus alpha. nR delta T, nR delta T, nR delta T upon 1 minus alpha. N, I don't know. R as it is delta T. Okay, but I don't know delta T also. 1 minus alpha. It is 1 minus 3, which is nR delta T by negative 2. Now, the problem is, okay, no, there is no problem actually. I think we can just substitute all these things over here now. Let's substitute all these things over here because I know Q is nothing but work done plus your delta U, plus your delta U. So what is delta U? Delta U is 5 nR delta T divided by 2. What is the work done? Work done is negative nR delta T by 2. Okay. This is equal to, the same thing, NC poly delta T. So NC for that polytropic process delta T. The best part is, as you can see, N delta T delta T delta T cancels off. Oh, brilliant. So what am I left with? 5R by 2 minus R by 2. So it is basically 5 minus 1 by 2 times of R is C poly. So therefore, the C of that polytropic process, 5 minus 1, 4, 4 by 2, 2. So it is nothing but 2R. So the polytropic process has a heat capacity, molar specific heat capacity of 2 times of R. And that is done and dusted. Mithil, just a refresh. I think it should work. It should not be a problem. Just refresh. Clear, guys, how to solve all these questions? These are all questions on processes which can be asked. I have done decent variety of questions, decent level of questions. We will do more practice, of course, later on. Okay. Now let's come to the last law of thermodynamics, which is called as the second law of thermodynamics. We have the simplified version without talking about entropy, enthalpy, Gibbs free energy, nothing like that. So in physics, you don't have entropy, Gibbs free energy and all of that. You just talk about a more mechanical aspect of it. Sir, please do not send it with you or any you. Most common of you will get the details of what are you saying, Mohammed? I didn't get you. Okay. This says that heat will naturally flow from hot body to a cold body and not the reverse, because otherwise it increases something called as the entropy, uh, uh, because that happens to increase the entropy of the universe. Entropy is basically a number associated with randomness, and the randomness is something which always increases in the universe. Let's not get there in terms of entropy. Let's understand it in terms of engines and refrigerator. Let's understand it. See, I'll tell you what this is all about. What this is all about. You might have seen your car has an engine, your bike has an engine, diesel generator has an engine. What does an engine exactly do? You might be wondering. What does an engine exactly do? If you have an engine, basically what you do is you supply heat, you supply heat by combustion, usually by some gases which are going to burn. This is going to be from some hot reservoir, like the hot gases, the hot fuel is going to burn. It is going to supply heat. From that heat, you will extract some work. So there will be some work which will be done, meaning the wheels will move, the vehicle will move front, some mechanical work is done. But don't expect all the heat to be converted into work. That is not possible. You will always see, no matter what you do, there will be always some heat which is rejected to the surroundings. So there will be some rejected heat. There will be always some rejected heat to the cold surroundings. Your outside air is cold, so this is rejected heat to your surrounding. It is impossible that you have a heat engine which says that whatever heat has been absorbed completely goes into the work done. That is impossible. You will always see some amount of heat which is going to be rejected. It is not possible to completely convert it into work. That is what second law is in terms of the explanation for an engine. Similarly, the reverse of an engine, the reverse of an engine is called as a heat pump or refrigerator, where you do work on it. You have to perform work on it. And then what it does is it will extract extract heat from a cold body, and it will give it release heat into a hot side. What does a fridge do? Inside it is cold, outside it is warm. Actually, heat should come from outside to inside, but then the whole point of a fridge is lost. What a fridge does is inside is cold, outside is hot. Instead of the heat coming from outside to inside, it makes sure the heat goes from inside to outside. But it can't happen naturally. It has to be artificial. So it uses something called as a heat pump, a motor. There is a compressor inside, which manually forces the heat from the colder side to the hotter side. Otherwise, heat should naturally flow from hot to cold. So naturally, it will not flow. Unnaturally, artificially, because of the work, you are able to do it. So this is also second law, but in a different way. Okay, I hope this is clear. This is what exactly has been mentioned. Kelvin Planck statement is basically for a heat engine. Kelvin Planck statement is basically for a heat engine. It is impossible for any device which takes heat and converts it into work. It takes heat and converts it into work. Not possible. always some heat will be rejected. That is number one. The other part is Clausius statement, which says it is impossible to construct or make a device which has no effect than to transfer the heat from lower temperature to higher temperature. Impossible to make a device which goes which makes sure the heat goes from cold side to the hot side without doing work. Impossible. You have to work on it so that the heat goes from cold side to the hot side. Otherwise, impossible. Is this clear, everyone? Yep. These are all the important things about the second law of thermodynamics. All right. So we are done with this, my dear students. What is this? We're done with this second law also and the theory part. Now, next time onwards, we'll be meeting for problem solving sessions. And of course, after a few days, if there are a couple of students who have some backlogs, we can start some backlog series as well. Not an issue. Okay. So if you have certain backlogs or certain chapters which you need help, specific type of problems, specific type of concepts, do let me know in the comments. I'll be more than happy to make those sessions, and make sure you're liking those comments so that more the votes, the more popular or probable that I will consider that session. Okay, take care. Make sure you're liking this video, subscribing to the channel, commenting below, and yes, remember the sale, the new year sale is ending 5th January. That's tomorrow. If you're not yet taken any course, bought any book, flashcards, test series, today is the right time, because tomorrow after midnight this offer will go away. You will lose the price benefit. I don't want you to lose that price benefit. If you're already a part of some batch, consider the All India test series, the flashcards, or even the PYQ books. If you have any one of them, check which other things you can best buy at this moment, because you are getting these awesome deals and I don't want you to unnecessarily pay extra them later on. Okay, because this offer is not going to come back now for a very long time. Bye bye. Have a great time and smash the like button. Thank you so much. The PDF, I will share it by tomorrow. Take care. Hasta la vista.